Hi, in this lecture we will see what vector spaces are. So vector space is one of the most important concepts as coming to linear algebra and in the exam point of view as well. So we will see in detail how vector spaces are defined. They have a very detailed, very long definition. So we will try to understand what the definition means, what are the properties of vector spaces, and how do we formally define a vector space, and what sets are vector space and what sets are not actually vector spaces. We will try to understand that. So let's start. So before jumping on to vector space, any vector space is defined on a field. Okay, so field is a concept of mathematics and vector space is a concept of linear algebra. So firstly, let's try to understand what a field means, and then we will see what vector spaces are, because every vector space will be defined on a field. Okay, so let's see the definition of field. A field F is a set. It is a set of elements. It will have certain elements. It might be a finite set, it might be an infinite set as well. So a field F is a set with two operations, addition and multiplication. So you will perform addition on the elements of the set and you can perform multiplication on the elements of the set. Two operations must be defined. So for any field you will have some set of elements and you must define two operations, addition and multiplication. Okay, with two operations, addition and multiplication, such that, okay, so these four properties must hold on any field. Addition and multiplication are commutative and associative, which means, let's say a particular field, okay, a particular field has certain elements, okay, let's say a1, a2 and so on, and okay, or let's say a, b, c and so on. Okay, A, B, C and so on. There are many elements, let's say, in this field. Then if I take any two elements, firstly two operations must be defined. Okay, so addition and multiplication, two operations must be defined on any field. And now both addition and multiplication should be commutative and associative, which means if you take any two elements inside the field, then their addition a plus b should be equal to b plus a, which means addition should be commutative. This is commutative, right? And addition must be associative as well, which means order of addition does not matter. So a plus b plus c should be equal to a plus b plus c. It doesn't matter which you are adding first. If you are adding a and b and then or if you are adding b and c, it doesn't matter. The answer should be same. Okay, so addition on any field must be commutative and associative, and also multiplication should also be commutative and associative, for which means a times b should be equal to b times a, and also a times b times c should be equal to a times b times c. Okay, so addition and multiplication both should be commutative and associative in any field. Okay, this is the first rule. We will see some examples, then it will become more clear. Second is multiplicative identity 1 should exist inside the field, and additive identity 0 must exist inside the field. Now here I am telling you the numbers 1 and 0, but it is not necessary that the number 1 and the number 0 should be present as the element in this set. What it means is there should exist one element which acts as the multiplicative identity, and there should exist an element which acts as an additive identity. Generally we call the multiplicative identity as 1 of the element of the set and additive identity as the 0 of the set. Now 0 can be anything, okay, so we just call it 1 of the set and 0 of the set. Okay, so we will call multiplicative identity as 1 of this field and additive identity as 0 of this field. Now what is the property of this multiplicative identity and additive identity? So for any field, multiplicative identity means what? It means that there must exist an element in the field. There should exist an element in the field. We will call this element 1. So it might be possible that the number 1 is the same element 1. Okay, it might be possible that something else is 1. Okay, but we will call it 1 for now. So the multiplicative identity means there should exist an element in the field such that when you multiply 1 with any number, with any element, when you multiply 1 with any element in the field, you will get the same element of the field, where A is any element in the field. For all A's, for every element A in the field, if you just multiply 1 with that element, you will get the same element back. Okay, so we must have an element 1 such that this property holds. Okay, and also additive identity must exist inside any field. Additive identity must exist means there must exist an element which we call the element as 0. We will call this element as the 0 of the field. So there must exist a 0 inside the field such that when you add this particular element to any element inside the field, when you add this 0 to any element inside the field, you will get the same element back for all the elements inside the field. Okay, so for any field, firstly, addition and multiplication should be defined for all the elements. Addition and multiplication both should be commutative, they should be associative, and there must exist a 1 inside the set and there must exist a 0. Now 1 is the multiplicative inverse and multiplicative identity, and 0 is the additive identity of the field. Okay, cool. The third property is every non-zero element has a multiplicative inverse. Every non-zero element must have a multiplicative inverse in a field, which means that what is multiplicative inverse? Multiplicative inverse so for any element inside the field, let's say for any element inside the field, let's say there is an element f, there is an element A inside the field f. For any element A, there must exist an element A inverse which is also inside the field. For any element A, there will be an element A inverse such that A into A inverse will be equal to 1. 1 is the multiplicative identity. 1 is not the number 1 here. 1 is the multiplicative identity. Whatever element is multiplicative identity. Okay, so if you are not able to understand it, let's say this is my set. Okay, and I'm just giving you a basic example of like real life example. Okay, so let's say this is my set and I'm calling this set as a field, and let's say it has some objects, real life objects. Let's say it has a pen, it has a pencil, and it has an apple, and it has an orange, and so on. Now for this field, pen might be the 0 of this field, which means pen might be the additive identity. Okay, and let's say apple is the multiplicative identity of this set. Then what will happen? If you multiply any element inside it with apple, you will get the same element back. And if you add any element with pen in this set, you will get the same element back. This, like, you will not be able to connect to it, but let's say addition and multiplication in this particular field is defined that way. Okay, addition and multiplication is defined that way only. Ki pen plus pencil will be pencil, pen plus apple will be apple, and so on. Which means pen is the additive identity and apple is the multiplicative identity. That's what I was trying to say. It is not necessary that the number 0 and the number 1 is present inside the field. Any element can be the 0 of the field, any element can be 1 of the field. And multiplicative inverse means for any element, let's say for any element pen, or no, let's not take pen, let's take let's say orange. Okay, and let us say orange times something else, orange times pencil is equal to apple. What does it mean? Let's say I defined multiplication such that orange times pencil is equal to apple for this field. What does it mean? Apple is the multiplicative identity, which means apple is the 1 of this field, right? Apple is the 1 of this field. It means that pencil is the inverse of orange and orange is the inverse of pencil inside this field. So for every element, a multiplicative inverse must exist, except the 0. So for the 0 of the field, the multiplicative inverse won't exist. Okay, so that is what they are saying. For every non-zero element, so for the 0 of the field, if the multiplicative inverse does not exist, that is okay. But for every non-zero element inside the field, the multiplicative inverse must exist, and it should exist inside the field itself. Okay, this is the third property. And the fourth property is distributive law must hold true. Distributive law must hold true. So what is the distributive law? Distributive law means for any three elements A, B and C inside the field, A times B plus C must be equal to A times B plus A times C. Okay, so the multiplication must be distributive over the addition. Okay, which means A times B plus C must be equal to A times B plus A times C for any element, for any three elements A, B and C inside the field. For any three elements A, B and C inside the field. Okay, so all these rules must hold true, then only we can say that a particular set of elements is a field. Okay, so now let's try to see some examples of field, like what are valid fields and what are like not valid fields. Okay, so all these are examples of fields. First is the real numbers. Okay, real numbers. All the real numbers, the set of all real numbers, it is an infinite field. It has infinite number of elements, right? There are infinite real numbers. Real number is any number, right? Like any positive or negative real number. Okay, it might be rational, it might be irrational, like 0, -1, minus pi, plus pi, 22 by 7. All these elements are present inside the real number set. And real number is a set, we already know. The real number is a set, right? And real number set is actually a field. It is actually a field as well. We can call it as a field. Why? Because all the properties will hold true inside this set. Think of it, okay, like what will happen? What is the first property? Addition and multiplication must be defined. So addition and multiplication is defined on real numbers, right? You can add two numbers, you can add two real numbers and you will get a real number. You can multiply two real numbers and you will get a real number. And hence addition and multiplication is well defined on real numbers. Now second property was addition and multiplication should be commutative and associative. That is very easy to see. For any two real numbers, we know that A plus B will be equal to B plus A. If you add any two real numbers, it will be commutative, we know that. And similarly associative also, the order of addition won't matter in real numbers, right? This will also hold true. Okay, I don't need to prove it, right? They are very basic. And similarly for any two real numbers, if you multiply them, the order doesn't matter, right? 2 into 3 will be equal to 3 into 2, right? So for any two real numbers, A into B will be equal to B into A, and hence multiplication is also commutative. And also multiplication will also be associative also. So in multiplication also the order doesn't matter. Okay, so for any real numbers, all these properties hold true. The second property was additive inverse and multiplicative inverse. Additive identity and multiplicative identity must exist. So what is the additive identity inside the set of real numbers? It will be the number 0 itself, right? Additive identity in the set of real numbers will be what? Additive identity in the set of real numbers will be the number 0 itself. The number 0 is present inside the real numbers, and the number 0 has that property. If you add it with any number, you will get the same number back. 0 plus pi will be pi, 0 plus 3 will be equal to 3, and hence the additive identity for the set of real numbers is the number 0. Now the multiplicative identity for the set of real numbers will be what? It will be the number 1 itself. It will be the number 1 itself, because if you multiply any number with 1, and 1 is a real number, plus 1, we are talking about plus 1, not minus 1, plus 1. Plus 1 is the multiplicative identity in the set of real numbers, right? Because if you multiply any number by 1, you will get the same number back. So additive identity exists and multiplicative identity exists. Now multiplicative inverse for every non-zero numbers should also exist. So for any number A, which is a real number, okay, for any number A which is a real number, 1 by A will also be a real number. Do you agree? If A is not 0. If A is not equal to 0, because 1 by 0 is not defined. 1 by 0 will be infinity, right? 1 by 0 is not defined, but except 0, for any number which is a real number, 1 by A will also be a real number, right? For example, let's say A is minus 5, then minus 1 by 5 will also be a real number, minus 0.2, right? So for any real number, 1 by A is also a real number, and 1 by A is actually the multiplicative inverse of A. It is the multiplicative inverse of A. How? Because A into 1 by A will always give you 1, which is the multiplicative identity, right? And hence for every number A in real number, its multiplicative inverse also exists, and that is also inside the same set, and hence the third property also satisfies. And distributive law, obviously it holds for real numbers, we know that. a times b plus c for any real numbers will be equal to a times b plus a times c. So distributive law also holds. And that is why set of all real numbers is a field. It is a field because all the properties hold true. Okay, all the properties must hold true. And we can say that the set of real numbers is a field. And this is the most used field. Okay, whenever we discuss linear algebra in this course, the mostly we will be using real numbers as a field only. Okay, we will be discussing vectors on real numbers. Okay, so the field will be real numbers in most of the cases in the entire course. And just understand that the set of all real numbers is a valid field. Okay, next let's look at the set of complex numbers. Okay, so set of complex numbers is also a field. Again, it will satisfy all the properties. So set of complex numbers, okay, so it will contain all the complex number like this x plus y iota, where x is the real part and y is the imaginary part. Okay, so it will contain all such possible complex numbers. So why is it a field? Again, let us check. So addition and multiplication is defined on imaginary numbers, right? You can add two imaginary numbers like this. Let's say we have an imaginary number and we have another imaginary number like this. Then we can add them and we will get 1 plus 6 iota, right? And similarly, we can multiply two imaginary numbers as well. 3 plus 5 iota times minus 2 plus iota. So we can write it like minus 6 plus 3 iota and then minus 10 iota. Then we will have plus 5 iota square, which is minus 5. So we will have minus 11 minus 7 iota like this. So we can multiply two complex numbers, we will get another complex number, and we can add two complex number and we'll get another complex number. So addition is possible on set of complex numbers, multiplication is possible on set of complex numbers. Now let us look at the properties. First is first is addition and multiplication should be commutative and associative. So just like the set of real numbers, here also like for any two complex numbers, we can say that a plus b will be equal to b plus a, and a times b will be equal to b times a, and same for associativity as well. A plus b plus c will be equal to a plus b plus c. And same for multiplication as well, AB times C will be equal to A times BC. Okay, so multiplication and addition is commutative and associative for complex numbers as well. Now the additive identity for complex number will be the zero complex number, which has the real part and complex part both has 0. So 0 plus 0 iota. Okay, this will be the additive identity. This will be the 0. So this is the additive identity of complex numbers, because if you add it to any complex number, you will get the same complex number back, and this is a valid complex number. It is present in the set of all complex numbers. And what is the multiplicative identity? It will be 1 plus 0 iota. 1 plus 0 iota, because if you multiply any complex number with 1, with the real number 1, which means 1 plus 0 iota, then we will get the same complex number back. So this is the multiplicative identity. Okay. Now coming to the inverse, again like the multiplicative inverse also exists for any number a, for any complex number a, 1 by a. 1 by a will also be a complex number, right? So for any complex number a, 1 by a will also be a complex number, and 1 by a will also be present in the same set, and hence 1 by a into a will become 1, which is the multiplicative identity, or 1 plus 0 iota, and hence like 1 by a is the multiplicative inverse for any number, for any complex number a, and hence multiplicative inverse also exists. And you can like the distributive property will also hold true. You can write a times b plus c as ab plus ac even for complex numbers. You can verify it even for complex number, this also holds true. So all the properties which hold true for real numbers, which are there for field, hold true for complex numbers as well, and hence complex number is also a valid field, the set of complex number. Okay. Next is the set of rational numbers. The set of rational numbers is also a valid field. You can check that. The number 0 here will be the additive identity. The number 1 will be the multiplicative identity. And if you add any two rational number, you will get a rational number again. You will never get an irrational number, right? If you are adding two rational numbers, you will get a rational number, and hence addition is well defined and multiplication is also well defined. If you multiply two rational numbers, you will get the rational number back. Now coming to inverses, for any number a, 1 by a. So for any rational number a, if a is a rational number, then 1 by a will also be a rational number, right? And hence for every number, multiplicative inverse which is 1 by a will also exist in the same set. So multiplicative inverse also exists, and commutativity, associativity, distributive property will hold true for rational numbers as well. So the set of all rational numbers is also a valid field. Next is finite field. So all these three were infinite fields. They were all infinite fields. They had infinite number of elements. There are infinite real numbers, there are infinite rational numbers, there are infinite complex numbers. But next is FP. Okay, FP is the finite field. It is called a prime order field. So this is not very relevant to exam perspective, but let me tell you what a finite order field is. So, or a prime order field is. Okay, here addition and multiplication are defined in a slightly different manner. So what will happen is, here we will have exactly p elements in the set. Here we will have exactly p elements in the set, and the number of elements will always be a prime number. Okay, and the addition and multiplication will be defined in a very special way. So addition and multiplication are always done modulo p. Okay, so how is this field defined? So let us define a finite field with a prime order 7, let's say. Okay, so it will contain the numbers 0, 1, 2, 3, 4, 5, 6. It will contain the numbers 0, 1, 2, 3, 4, 5, 6. Only 7 numbers will be present inside it. Okay, and now addition for any two numbers here will be defined like this. It will be, so if you are trying to add any two numbers, you will have to do it modulo 7. So the addition of any two numbers a and b is defined as a plus b modulo 7. Okay, and similarly the multiplication is also defined like this. The multiplication of any two numbers will be defined like a into b modulo 7. So we just defined addition and multiplication like this. Why? So that every number, whenever you are adding it, if you are taking remainder when divided by 7, it will be again a number between 0 and 6. So it will again lie in the same finite set. And same for multiplication. For any number, if you multiply it and take modulo 7, it will again lie in the same finite set. Okay, so this is how addition and multiplication are defined for this finite, for this field. Okay, this is a 7 order prime field. Okay, so now let's check. So again, a plus b will be equal to b plus a, right? Because a plus b modulo 7 will be equal to b plus a modulo 7, and similarly a into b will be equal to b into a, because a into b modulo 7 will be equal to b into a modulo 7. And then associativity also holds true. A plus b plus c will be equal to a plus b plus c, because b plus c modulo 7 plus a modulo 7, it doesn't matter when you are taking modulo 7, right? Essentially you can take the modulo 7 at the end after adding all three of them, so it doesn't matter. Okay, and same for multiplication as well. A into b times c will be equal to a times b into c. Here also it doesn't matter where you are taking modulo 7, you can take it at the end. Firstly multiply all three of them, and then at the end you can take remainder when divided by 7, you will get the same answer. And hence addition and multiplication are both associative as well. Okay, so now let's try to see the additive inverse. Okay, additive identity. So the additive identity in this field will be, additive identity will be the number 0. Why? Because 0 plus any number a will give you the same number a. Why? Because 0 plus any number a, how is addition defined? It will be 0 plus a modulo 7. 0 plus a modulo 7, which will be a modulo 7. Okay, because 0 plus a is a. So for any number a inside this set, if you take modulo 7, you will get the same number back. Right, because all the numbers inside this set are 0, 1, 2, 3, 4, 5 and 6, and any number you divide by 7, the remainder will be the same number again, right? So there is no number which is bigger than 7, and hence 0 is the additive identity inside this set. And similarly the multiplicative identity will be 1. Multiplicative identity will be 1, because 1 into a will be a only here, because how is the multiplication defined? It will be 1 into a modulo 7, and 1 into a will be a only, and a modulo 7 again is a. Okay, now inverse. So inverse is slightly tricky here. Why? Because let's try to find out. Okay, so see, multiplicative inverses only exist for non-zero numbers, right? So for 0, inverse will not exist because 0 is the additive identity. So for non-zero numbers only, multiplicative inverse will exist. So let's try to figure out the multiplicative inverse for 1. So 1 into what number will give you 1 again? So 1 into 1 modulo 7 will give us the same number 1 again, right? And hence the multiplicative inverse of 1 is 1 itself. The multiplicative inverse of 1 is 1 itself, which exists inside the set. Now for 2, what number do I multiply and then modulo 7, I'll get 2 again. For 2, what number do I multiply? And if I take modulo 7, I'll get 2 again. So if I do 2 into 1, I'll get 2. If I do 2 into 3, I'll get 6. If I do 2 into 4, I'll get 8. And 8 modulo 7 is 1. So 4 is not the multiplicative inverse of 2. And if we do 2 into 5, which is 10, again for 10 also that won't happen. Okay, 2 into 4 is 8. And 2 into 5 is 10. And 2 into 6 is 12. Okay, so we want to figure out what number do I multiply with 2 and take modulo 7 and I get the multiplicative identity, which is 1, right? That will be the multiplicative inverse. So 2 into 2 if we do, we'll get 4. 2 into 3 we'll get 6. 2 into 4 if we do, we'll get 8. And 8 modulo 7 is 1. The remainder when 8 is divided by 7 is 1, right? And 8 modulo 7 will be 1, and hence 4 is the multiplicative inverse of 2. 4 is the multiplicative inverse of 2, and you can say that 2 is the multiplicative inverse of 4. So we can write it this way. The inverse of 1 is 1. So multiplicative inverse of 1 exists, and multiplicative inverse of 2 here will be 4, and the multiplicative inverse of 4 will be 2 in this set. Okay, so this number for 0 it won't exist anyway. For 1 we have 1, for 2 we have 4. Now let's check 3. So what is the multiplicative inverse of 3? So 3 into what number modulo 7 will give us 1. This is what we want to find. So if we do 3 into 5, 3 into 5 is 15. 15 modulo 7 is what? What is the remainder when 15 is divided by 7? It is 1. And hence 5 is the multiplicative inverse of 3. So in this set, the multiplicative inverse of 3 is 5 and the multiplicative inverse of 5 is 3. Okay. And now coming to 6. So 3 and 5 are done. Now for 6. So what is the multiplicative inverse of 6? So what number do I multiply with 6? And then take modulo 7 so as to get 1. So if you multiply it by 6 itself, 36 modulo 7 is what? 36 modulo 7 is 1, because 7 5s are 35. So remainder will be 1, right? So 6 is the multiplicative inverse of itself. Okay, so 6 is also done. So for every number multiplicative inverse, a unique multiplicative inverse exists. And hence all the properties satisfy for this set as well. This was a set containing only 7 elements. It was a finite field. It is a finite field. The only difference is we are not having the convention addition and multiplication. Addition and multiplications are defined modulo the prime number. Okay, and if the prime number is 7, then you will take the numbers from 0 to p minus 1, and this will be a field because of these reasons. Okay, all the properties satisfy here. Okay, so this is a finite field. It is called a finite prime order field as well. Here the number of elements must always be prime, then only this will work. Okay, otherwise inverses won't exist, and so on. So these were all examples of field. So what is not a field? Okay, so what is not a field? Let's take an example which is not a field. So if I take the set of, let's say, integers. If I take the set of integers, is it a field? So for integers, addition is defined, multiplication is defined, and addition is commutative and it is associative, and multiplication is also commutative and it is associative as well. The first property holds true. For integers, even the additive identity exists. The additive identity 0 exists, because if you add any 0 to any integer, you will get the same integer back. And even the multiplicative identity also exists, right? Because if you multiply any number by 1, any integer by 1, you will get the same integer back. So the existence of additive identity and multiplicative identity is also there. But the property, like the existence of multiplicative inverse, that is tricky. The existence of multiplicative inverse is not there. Why? Because for any number a, which is an integer, what do you multiply it with so as to get the multiplicative identity back, which is 1? You have to multiply it with 1 by a. So for 3, that number has to be 1 by 3. Then only you will get 1. right? But 1 by 3 is not an integer. 1 by 3 is not an integer. It is not present in the same field, and hence for any number multiplicative identity does not exist, right? For all the numbers multiplicative identity must also exist in the same field. But let's say if you take any integer, let's say -7, for -7 there is no integer which you can multiply it to so as to get 1 back, right? So multiplicative inverse for most of the elements doesn't exist, and hence set of integers is not a field. Set of integers is not a field, okay? But set of rational numbers is a field, set of real numbers is a field, set of complex numbers is a field, but set of integers is not a field. Even I hope this makes sense, right? Cool. So these were examples of field and non-fields. Why did we discuss it? Because the definition of space, the vector space, that's what we want to get into. In definition of vector space, it will be defined over a field. So let's look at the definition of vector space now. Okay, now let's look at the definition of a vector space. Okay, so a vector space is a non-empty set. It is also a set. So vector space is a set V over F, which means every vector space is defined over a field. So what do we mean by over a field? We will see shortly. So the elements of field will also be important. Okay, so every vector space will be defined over a field having two operations. It also has two operations. For example, field every field has two operations, addition and multiplication, right? And similarly, every vector space also has two operations defined on it, which means every element of this set you can perform two operations on it. First is addition, which means you can add, and this particular addition operation is V cross V, which means you have to take one element in the vector space and then another element in the vector space and then add them. So it is a function, right? You have to take one element from the vector space and another element from the vector space, and when you add them, you will get another element in the same vector space. Okay, this is how functions are defined. This is the domain and this is the range, right? So domain is V cross V, which means you will take two vectors, right? Elements of a vector space are called vectors. Now this vector is different from the definition of vector that we were using like till now. Okay, here in a vector space, an element can be anything, any object, just like apple, bananas, oranges, which I told you right now, right? So again, in a vector space, the elements can be anything. They need not be the Euclidean vectors which we were seeing. Okay, so I'll come to that. But a vector space will contain elements, and these elements are called vectors, and addition is defined over two vectors. So you take any two vectors, you add them, and you'll get another vector in the same vector space, which means it is inclusive in some sense, right? When you add two elements from a vector space, the result should also be in the same vector space. Okay, so V cross V to V. So addition should be defined, and second is scalar multiplication. See, very important difference in field. Normal multiplication was defined when you which means you have to multiply the two elements of the field. Here you don't have to multiply the two elements of a vector. We are not multiplying elements of like two vectors together. It is a scalar multiplication, which means it is F cross V. F cross V means you take any element from the field and that element will be a scalar, right? So you can multiply any element from the field and multiply it with any vector, and the resultant should also be a vector in the same vector space. Okay, so let me give you an example of this. Okay, so let's say I define a vector space which is the set of real numbers. Vector space is a set of real numbers over the field. Field is also the set of all real numbers. Field is also set of all real numbers. This is possible. So I just took the vector space as the set of real numbers, which means they are all elements, right? They are all real numbers, and I defined it over the field, which is also the set of all real numbers. Now what does it mean? There are two properties. The first property is addition, which means if I take any two elements from the vector set, they will be called vectors. So vector A and vector B, which means if I take any two elements from the vector space and if I add them, then the resultant should also be in the same vector space. So if I add any two real numbers, the result will also be a real number. So that is satisfied. And second property is if you take any element from the field is this one. So if you take any element from the field, let's say k is the element that we took from the field, any element. And if you multiply it with any vector, here vector is what? An element in R. So again, it will be k times A. So then the resultant, this result should also be in the part of the same vector space. So this is also satisfied. If you take any real number from here and you multiply it with any real number, you will get a real number which is also a part of the same vector space. Okay. So these two properties must be defined. So this is here what we were doing, here we were taking, here the vectors were also real numbers and the field was also real numbers. But in real life, spaces will not be this simple. Okay, so let me give you one more example of space. Now I am defining the space as R square, which means the Euclidean space, x axis and y axis, which means it will have two values, x comma y. Okay, R square means it will have two values, x comma y. So R square means it is the set of all values x and y, where x is also a real number and y is also a real number. Okay, it is a set of tuple. Tuple means what? It will be containing two values. In Euclidean space, when we have x coordinate and y coordinate, you will have two values, right? X and y. So here R square is a set of all such pairs, 1 comma 1, 1 comma pi, 3 comma 2, minus 1 comma minus 7. Both are real numbers. Okay, so this is the vector space right now. And we can define it over a field. Field is also, let's say, the set of real numbers. Field is also a set of real numbers. Okay, so here vector is what? Vector is having two components. Here vector was having only a single component. Here the vector was what? Set of all real numbers x, such that x is a real number, right? But here the set of, in R square, the vector space contain vectors which are tuples, which have two elements, which means it is in two-dimensional space, right? So here the vectors are in two-dimensional space. They have two components, x and y both are real numbers. Okay, so this x and y, they are both will be part of the same field. Here also the element x was part of the same field. Here also, if I am defining R square, both the elements will be the part of the same field. Okay, so this is my vector space. Now addition, let's look at the properties. First is addition and second is scalar multiplication. So addition means what? If I take any vector v1, it will have two components, x1 and y1, which means it will be a tuple containing x and y, x1, y1. And if I add it with another vector v2, which is also a part of R2, which means it will also have two components, x2 and y2. So addition should be defined. So let us say we defined addition like x1, it will be another tuple, x1 plus x2, y1 plus y2, standard vector addition. So I just added this vector with this vector. So the result will be another vector, which is x1 plus x2, y1 plus y2. And this particular vector will also be a part of R2, because if you add two real numbers, you will get another real number. If you add two real numbers, you will get another real number. This is also real number, comma real number. So this will also be a part of R2. So addition is defined. You take any vector from the space, and if you take another vector from the space, their addition will be also a part of the same space. Okay. So addition is defined. Second is scalar multiplication. Scalar multiplication means what? You take any element from the field. You take any element from the field. So if you take any element from the field, let's say k, and if you multiply it with any vector, okay, if you multiply it with any vector from R2, then the resultant should also be the part of the same space, which also holds true, right? If you multiply any, let's say, if you multiply any vector x1, let's say x1, x2 is already, so x3 comma y3. Okay, let's say I took a vector x3 comma y3, and if I multiply with a scalar k, I'll get another vector k times x3 comma k times y3. This is also a vector, right? This is also a valid vector which will be present in R2. Why? Because k times x3 is also a real number, k times y3 is also a real number. This will also be present in the same vector space, and hence R square is a space until now. Okay, both these properties are satisfied. We have addition well defined and we have scalar multiplication well defined. Scalar multiplication means you take an element from the field, you multiply it with any element from the vector space, and you will get an element in the same vector space. And addition means you take a vector element from the vector space, You add it with another element in the vector space, the result should also be an element in the same vector space. Okay, so a vector space will be defined over a field such that these two properties hold, and also it satisfies the set of axioms for vector space. Okay, so every vector space must satisfy a set of 10 axioms. Okay, in some literature you will find there are 8 axioms, in some literature there are 10 axioms, essentially they are same. Okay, so we will see all the set of axioms which every vector space must satisfy. These are not sufficient. Addition and scalar multiplication should be defined, and also every vector space must satisfy a set of rules. So now let us take a look at those rules. Cool. So now let's see the set of axioms or the rules which every vector space must satisfy. Okay. So there are 10 rules. We will see all of them one by one. So for all u, v and w in the vector space, so you are taking vectors u, v and w from the vector space, and a and b for all elements a and b in the field. So here when in all these axioms, u, v and w will be belonging to the vector space, and vector space is defined over the field. So a and b will be the scalars. They are the scalars taken from the field. Okay, so a and b are from the field, u, v and w are from the vector space. So the following conditions must hold true. First is closure over addition. Closure over addition, which means if you take any two vector in the vector space, then their addition must also be in the same vector space. If you take any two vectors from the vector space, then their addition must also be in the same vector space. Okay, this thing we have already seen. So addition should be well defined, and also for any two vectors in the vector space, their addition must be the part of the same vector space. And same as closure under scalar multiplication, which means for any element from the field, if you take any element from the field and if you multiply it with any vector from the vector space, then their product must be the part of the same vector space. Okay, these two things we have already seen. These are the most basic conditions, right? Closure under addition and closure under scalar multiplication. Okay, now next is commutativity of addition. So the addition, when whatever addition operation you are defining over the vector space, okay, whatever addition operation you are defining over the vector space, that addition operation must be commutative. Okay, it is like the same condition that we saw in field also, right? So similar condition is present here also. So for any two vectors in the vector space, if you are adding these two vectors, it should be commutative. U plus v should be equal to the v plus u. Both the vectors should be same. Okay, so apple plus orange should be equal to orange plus apple, whatever it is. Let's say it is grapes. So then both of them should be equal to grape. Okay, the addition should be defined like that. Okay, so addition must be commutative. U plus v should be equal to v plus u. Associativity of addition. So addition must be associative also. The same two rules we have seen for field also. So like in field also, addition must be commutative and associative, but the difference is in field we had multiplication also defined, but in vector spaces multiplication is not defined. We are never saying that you should be able to multiply two vectors. We are never saying we should be able to multiply two vectors. The operation that we are saying is scalar multiplication, which means you should be able to multiply a scalar from the field to a vector in the vector space, right? K times v we are saying, or a times u, which means scalar multiplication should be defined. An element from the field should be able to multiply, you should be able to multiply an element from the field to an element in the vector space. But two elements in vector space, there is no restriction. You don't need to multiply them. You don't need to define multiplication of vectors. That is not required. Okay, so only addition is required, and addition should be commutative and associative. Okay, which means u plus v plus w should be equal to u plus v plus w. The order should not matter, and it should be associative. Okay, next is existence of the zero vector. So in every vector space, the zero vector must be present. Now again, the zero vector or the zero element can be any element. It need not be the number 0. It can be any element, but it must have the property that if you add it with any other vector, you will get the same vector again. Okay, we already know what additive identity is, right? In field, same concept apply for vector spaces as well. So in vector space also there must exist an element inside it which when added to any other vector you will get the same vector back. Okay, so one such vector must exist and we will call it the zero vector. Okay, and it is also called the additive identity. So there must exist an element 0. We will call it the zero element or the zeroth vector or the zero vector. There must exist a zero vector in the vector space such that if you add any vector from the vector space and if you add it with the zero vector, you will get the same vector back. And this is also called the zero vector. Okay, the zero here is called the zero vector or the additive identity. So additive identity must exist. Okay, so these are five axioms and we have 5 more axioms. Next is existence of additive inverse. Okay, here notice that multiplicative inverse is not a property. Okay, because we are not defining multiplication of two vectors. Okay, we are only defining addition of two vectors, and scalar multiplication is defined. Okay, so existence of additive inverse, what does it mean? For every element in the vector space, for every vector in the vector space, there must exist another vector in the same vector space, and if you add them both up, you will get the zero vector. Okay, so for every vector in the vector space, there must exist another vector which is called minus of u. So for any vector u in the vector space, there must exist another vector in the same vector space which is called minus of u. That also must be part of the same vector space, such that when you add u and minus of u, you will get the zero vector. Okay, this is called additive inverse. So additive inverse must also exist. Okay, for every element. Cool. Next is identity element of scalar multiplication. We are not saying multiplicative identity. Multiplicative identity is different. Multiplicative identity is an element 1 which when multiplied by same element in the field, right? Because there we were multiplying two elements from the same field. But here we are multiplying the element from the field to a vector. And hence we are saying identity element of scalar multiplication, which means there must exist an element in the field. There must exist an element in the field which is called the element 1. So element 1 must exist in the field such that when it is multiplied with any vector, you will get the same vector back. Okay, so it is called the identity element of scalar multiplication. So there must exist an element 1 in the field such that when you multiply 1 with any vector, you will get the same vector back, because only scalar multiplications are defined on vector spaces, right? So this is the identity element of scalar multiplication. Okay, I will again, we will see lots of examples on vector spaces and I will reiterate on all these properties. Don't worry about it right now. Let's first read all of the properties or the axioms. Then with examples, I will go over them again and again. Okay, don't worry about it. Cool. Next is distributive of scalar over vector addition, which means if you are multiplying as any scalar, scalar is always taken from the field. Here A is taken from the field, right? We already know this. A is taken from the field. So A times U plus B should be equal to AU plus AV, which means if you are taking A and if you are multiplying it with the addition of U plus V, it should be equal to AU plus AV, which means the scalar multiplication should be distributive over the addition. The scalar multiplication should be distributive over the vector addition. And similarly, the vector addition should be distributive over, the scalar addition should be distributive over the scalar multiplication as well. So A plus B times U should also be equal to AU plus BU. So both way distribution should work, right? A times U plus V should also be equal to AU plus AV, and A plus B times U should also be equal to AU plus BU. So both these rules must satisfy. So distributivity of scalar over vector addition should also happen, and distributivity of field addition over vector should also happen. Okay, cool. And the last property is associativity of scalar multiplication. So scalar multiplication should be associative, because we know that in the field scalar multiplication is defined. If you take any two elements of a field, their multiplication is defined. For vector space it is not true, but for field it is true. So when you are multiplying any vector with two scalars, let's say I took a vector from the vector space and I want to multiply it with a scalar A from the field also and a scalar B from the field also, then order should not matter. Okay, so associativity of scalar multiplication means A times BU should be equal to AB times U. here, like it doesn't matter which you are multiplying first. You can multiply b with the vector first and then a, or you can multiply a with the vector first and then b, or you can multiply a and b together and then multiply it with the vector. The answer should be same. Okay. So these are the 10 axioms every vector space must satisfy. So now we will see all of these properties with an example. Okay, let's look at an example. So my claim is I'm defining a vector space, okay, R2. R2 is a vector space over R. Here R is a field, R is a set of all real numbers. R is a field, set of all real numbers. We know that set of all real numbers is a valid field, right? It satisfies all the properties of a valid field. So it is like, okay, set of all real numbers. And R2 is what? It is a set of pair of real numbers. It is a set of pair of real numbers, which means it is a set containing pairs of x and y such that x and y both are real numbers. This is what R2 is. And actually every pair in R2 can be drawn on a graph also. It is like a vector. It is like a two-dimensional vector, right? It is, you can also call it like set of all two-dimensional vectors. Actually set of all two-dimensional vectors is defined like this only, right? It is R2, right? We have seen this already, which means R2 means it is like you can draw it on a paper like this. It will have an x component and a y component, and all the points inside it is R2, right? A point here, this, like it will have an x component and a y component, so it is a pair. And hence the dimension of R2 is 2. It will have two independent entities. One is x and one is y. It will have two independent entities, and that is why the dimension of R2 is 2. Okay. So it will have two values x and y. So this is a set. Now we need to verify that it is a space or not. Okay. So we can call this particular point as, let's say, -5, 4. Okay. So and so on. We can actually draw all possible points in R2 on this plane. Okay. Cool. So we need to verify that R2 is a valid vector space or not. So firstly, addition is well defined on vectors, right? Like if I'm saying this is all two-dimensional vectors, we already know vector addition and scalar multiplication are well defined. So let us use the same definition of vectors. So I am defining addition and scalar multiplication. See, whenever I am saying I have a vector space, I have to define the addition and scalar multiplication, right? So let us define it in the same way, okay? So for any two vectors in R2, we will define their addition like this. So x1, y1 plus x2, y2 will be x1 plus x2, y1 plus y2. This is how addition is defined. So we have defined addition, well defined. It is so we take one vector from the vector space. This is the vector space, right? R2. This is the vector space. So we take one vector from the vector space and we add it with another vector from the vector space. We will get another vector. The result will be something from the vector space itself. And we can define the scalar multiplication also. So this particular vector space is defined over the field, the set of real numbers. So we have to take any real number, which means any real number, let's say k. So k times x, y. So scalar multiplication is also well defined. We will call it k times x and k times y. So we are just doing scaling of the vector. If x, y is a 2D vector, we are doing its scaling, right? So it will be scaled by the multiplication factor of k. So what we are doing, we are taking a number from the field. We are taking an element from the field and we are multiplying it with a vector and we are getting a vector back. Cool. Now let's look at the properties one by one. So the properties, all the properties must be satisfied. First is closure under addition and closure under scalar multiplication. So they are very simple. Obviously, we can see here in this example. First property is satisfied. Closure under addition. Is satisfied. Why? Because when you add two vectors x1, y1 and x2, y2, since x1 and y1 both are real numbers and x2 and y2 are also real numbers, their addition like x1 and x2 will also be real number and y1 plus y2 will also be real number, which means this also will be a part of R2. This also will be a part of R2 and hence it is closed. It is closed, which means if you add any two vectors, you will get another vector in the same vector space. For any two vectors, you can find it, right? You can take an example as well, right? You can say 3, 6 when added with, let's say, minus 7, 5. We will get another number, right? Like minus 4, 11. This is again the part of R2. Okay, so closed under addition. Second is closed under scalar multiplication. Closure under scalar multiplication, again that is also satisfied. These are very basic properties, okay? By the definition only you can see they are satisfied. So again, like if you multiply any number from the field, let's say pi, times any vector from the R2, let's say 3 by 7, 2, then the answer will be 3 pi by 7, 2 pi. This is also R comma, this is also real number, this is also real number. So this particular vector is also a part of R2, and hence closure under scalar multiplication is also there. Second property is also satisfied. Now let's look at the properties. So commutativity of addition and associativity of addition. Commutativity of addition and associativity of addition, this is very simple. Like commutativity of addition and associativity of addition will also be there, because these properties we have already proved for vectors also. For vector, we are doing vector addition only, right? This is vector addition and vector scalar multiplication. So commutativity of vector addition is something that we have already proved, and associativity of vector addition is something that we have already proved. Of addition. So both the properties are also there, also holding. Because x1 y1 plus x2 y2 will be equal to x2 y2 plus x1 y1, right? Like because it will be x1 plus x2, y1 plus y2, and that will be x2 plus x1, y2 plus y1. So both are same, and hence commutative and associativity is also there for vector addition. So these properties are also satisfied. Now let's look at the next property. Next is existence of zero vector. So is there any zero vector inside this vector space? Is there any zero vector inside this vector space? Yes. The zero vector is present inside the vector R2, and that particular vector is the element 0, 0. This is the zero vector, right? Because if you add 0, 0 to any vector x, y, you will get the same vector x, y back, and hence 0, 0, which means this point. This point is the additive identity. This point is the additive identity. You add this particular point to any to any of the other vectors, you will get the same vector back. Okay, and hence 0, 0 is the additive identity. Cool. So additive identity, which means the origin or 0, 0 must be present. Okay, in the space, in the vector space, and in R2 it is present. Okay. And what is the next property? The existence of additive inverse, right? Additive inverse, yes. For every element there must be an additive inverse. So for any element u, which is, let's say, x, y, for any element u, x, y, its additive inverse, which means minus of u, will be what? It will be minus of x, minus of y. So if x, y is in the R2, then minus of x and minus of y is also in the R2, right? For minus 5, 4, its additive inverse will be 5, minus 4. This point, this will be the additive inverse, right? Because if you add minus 5, 4 to 5, minus 4, you will get the origin, which is the additive identity, right? So for any element in the vector space, for any vector in the vector space, its additive inverse also exists in the same vector space. This is also satisfied. So this also is a part of the vector space R2, and hence additive inverse exists for every element. Okay. Okay. Now let's look at the next property. Identity element for scalar multiplication. So in the field there must exist the identity element. So in the field here, field is R. The identity element for scalar multiplication exists, and that is the real number 1. So real number 1 exists in the set of real numbers, which is the field here, and if you multiply any vector with 1, you will get the same vector back, right? And hence identity element for scalar multiplication also exists. Okay. The next property is distributivity of scalar over vector addition and distributivity of field addition over vector. This is very simple. You can like property number 8 and 9 are distribution. Okay. So for any two vectors, what will happen? A times u plus v will be equal to au plus av. Right, it is very easy to prove because u plus v will be what? Let's say u is x1 comma y1 and v is x2 comma y2. Then u plus v will be x1 plus x2 comma y1 plus y2. And if you multiply it with a, you will get a times x1 plus x2 and a times y1 plus y2. And you can write it as ax1 plus ax2 and ay1 plus ay2, which is nothing but au plus av, right? So that very simple proof, you can do that on your own. Similarly, this thing also can be proven. A plus b times u will be equal to au plus bu. Okay, this is also very easy to prove because a plus b times u will be what? A plus b times x1 comma a plus b times y1, which is nothing but ax1 plus bx1 ay1 plus by1, which is nothing but au plus bu. Okay, so these two proofs you can do very easy. Okay, so distribution, both the distributive properties also hold true. And the last property is what? And the last property, okay, all the axioms must satisfy, then only a particular space is a vector space, a particular set is a vector space. Last property is associativity of scalar multiplication. So if you are trying to rescale, so it is also called rescaling, right? Whenever you are trying to multiply a vector with a scalar, you are scaling it. So if there is a vector minus 5 comma 4, if I multiply it with 2, I am just scaling it, I am just stretching it or compressing it, right? Scaling. So if I am trying to scale it 2 times, it doesn't matter which scaling I am doing first. So let us say for this vector I am trying to scale it by 2 times and then again 2 times. So it doesn't matter which 2 I do first, or I can immediately scale it by 4 times, then also I'll land at the same place, right? So yes, this property also holds true. A times b times u will be equal to ab times u. Okay, so rescaling also works. This is one of the most basic vector spaces. Okay, R2, all the 10 properties hold true, and hence yes, R2 or the Euclidean space, okay, with like the coordinate space with 2 axes, x comma y, is a valid vector space. Is a valid vector space because of lot of properties. Because the origin is present, additive inverse is present, associativity holds true, everything holds true, and hence R2 is a vector space over R. Okay, and what is the dimension of this vector space? The dimension of this vector space is 2, because there are two different values, two different independent values which you can have in every element of this vector space, right? We will see this dimension thing again and again, okay, later in the coming lectures also we will be seeing it. But I hope you are getting the idea. There are two independent values here. Okay, x can be any real number, y can be any real number from the field, and that is why the dimension is 2. Okay, so R2 is a valid vector space. But now an interesting question arises. There are 10 such properties. How do I remember them for the exam, right? You need to remember all of them, because even if one of the property fails, generally it will be very easy to see that a particular space is a vector space or not. We will be seeing a lot of questions in this lecture. Okay, just wait. We'll be seeing at least 10 questions and we'll try to see they are vector spaces or not. But the idea is, the main point is, how do I remember these 10 axioms or the 10 properties? So I have come up with a beautiful rule. You can using that rule, you can remember these 10 properties. So let's see that. Firstly, I want to remember these 10 properties. How do I do that? So it's very easy to remember these 10 properties just by using the word vector itself. Okay. So the word is vector. Now what does it mean? Okay, so firstly we have V, which means vector addition. Okay, E is for existence, C is for closure, then T is for two distributive properties. It is not very straightforward, but this is the best we can come up with. Two distributive properties. Okay, then we have O is for one or the identity, multiplicative identity, one multiplicative scalar multiplicative identity, it is the scalar multiplicative identity. It is also called the element 1, that's why 1. Okay, and R is for rescaling. Okay, so first is vector addition. So vector addition, there must be two properties which must satisfy in a vector space. The vector addition must be commutative and it must be associative, right? So the vector addition must be commutative and associative. These are the two rules. Then second is existence. So in vector spaces, there must exist an additive identity. There must exist an additive identity, which means the zero vector. There must exist the zero vector, right? And also there must exist additive inverse. Additive inverse for every vector. Okay, so there must exist an additive identity and there must exist an additive inverse for every vector in the vector space. Okay, next is closure. So every vector space must be closed under vector addition and scalar multiplication. Okay, so it must be closed under vector addition and scalar multiplication. So this abbreviation will just help you to remember the properties. Okay, in exam if you forget some, then you can remember it using this way. Then there are two distributive properties, we know that. So one is the distribution of scalar on vector addition, which means a times u plus v should be equal to au plus ab. And the second distributive property is what? The distribution of scalar addition over scalar multiplication, which means a plus b times u must be equal to au plus bu. Okay, so there are two distributive properties. There is one multiplicative identity, okay, one scalar multiplicative identity, which means there must exist the number 1 or there must exist the multiplicative identity in the field, okay, such that 1 times any vector is the same vector. Okay, and then finally we have rescaling, which means if you rescale multiple times, then the order is irrelevant. It means that a times bu should be equal to ab times u and it should be equal to b times au. It doesn't matter in which order we are scaling, the final vector must be same. Okay, so in this way, using this acronym vector, you can actually remember all the 10 properties. Okay, 1 2 3 4 5 6 7 8 9 and 10. Okay, and always remember that in the first 4 we have two properties. So vector addition we have two properties, existence we have two properties, closure we have two properties, and there are two distributive properties. Okay, and then we have one multiplicative inverse and one rescaling. So this way we can remember these 10 properties, and for every vector space all these properties must satisfy, then only it will be called a vector space. Okay, so let's see more examples on vector space and we will try to see like all these properties satisfy in the vector spaces or not. So let's look at the first example. First is the Euclidean space Rn. We have already seen R2, the second Euclidean space, the two-dimensional Euclidean space, which contains all the 2D vectors, right? X comma y is a vector space, and similarly any Rn, we have already seen R over R. We have already seen this one, so which is nothing but R1, right? R1 is R only. It just has a single component, a single real number. We have also seen R2 over R. This is also a vector space, right? And similarly, any Rn, any n-dimensional Euclidean space, which means a set of all n-dimensional vectors, it is also a vector space over the set of real numbers. Okay, And it is very easy to verify. If I just try to see all the properties, we already know how to add two n-dimensional vectors, right? So what is Rn? It is the set of all pairs like x1, x2 and so on xn, such that all these xi's belong to real number, okay, where I is from 1 to n. This is what this set is, Rn. So it will have n different components, n independent components, and hence this particular vector space will be n dimensional. Its dimension will be n, because there are n different values which you can fill. They are all independent of each other, okay. So yep, it is an n dimensional space. This was one dimensional, this was two dimensional, and this is n dimensional, okay. It has n different independent components, okay. Cool. So how do we prove this is a vector space? Firstly, addition and scalar multiplication should be well defined over R. So firstly, addition is very simple. You can add two vectors and then the resultant is very simple to calculate. Just like R2, we will write it here. So we will say x1, x2, xn. Let's say this is the vector u and the vector v is y1, y2, yn. Then the vector u plus v will be defined by x1 plus y1, x2 plus y2, xn plus yn, okay. And scalar multiplication, which means from the field you take any scalar, k times u is also well defined. It is k times x1, k times x2 and so on, k times xn. So addition and scalar multiplication are well defined here. Now you can verify the properties. First property is V, which means vector addition. Vector addition must be associative and it must be commutative. Again, by the same proof, you can say that here also vector addition is distributive and commutative, okay? Distributive and commutative both. Second is existence of additive identity. Additive identity is the vector 0, 0, 0, the origin, right? In the n dimensional space, the origin. So 0, 0, 0 n times this vector is the additive identity, because if you add any vector to this vector, you will get the same vector back. So additive identity exists. And also the additive inverse for every vector in Rn also exists in the same space. It will just be the vector for any vector u. The vector minus u also exists, and the minus u vector will be minus of x1, minus of x2 and so on, minus of xn. Because if you add this vector to u, you will get the 0 vector back. And hence additive inverse for every vector also exists, okay. So V is satisfied, E is also satisfied. Next is closure. Closure is very simple. Closure is the simplest one, right? If you add any two vectors, the resultant is also an n dimensional vector, that is also part of Rn. And if you multiply any vector by k, then the resultant is also an n dimensional vector. All numbers are real numbers, that is also part of Rn. So it is closed under vector addition and it is closed under scalar multiplication both, and hence closure is also satisfied. Next is two distributive properties. You can prove the distributive properties here very well, like both the distributive properties, the distribution of you can say that a plus b times u will be equal to au plus bu, and you can prove it on your own as a homework, okay, like just like in 2D space you can prove it here as well. And similarly a times u plus v will be equal to au plus av. Okay, both the properties will satisfy. So the two distributive properties satisfy for all possible vectors and all possible values in the field. Okay. Next is 1. Does 1 exist? Does the scalar multiplicative identity exist in the field? In the field of real numbers, the number 1 exists. And the number 1 will have the property that if you multiply any vector by 1, you will get the same vector back. And hence 1 is a part of the field. And hence the scalar multiplicative identity also exists. And last is rescaling. Also rescaling will be satisfied here. AB times u will be equal to a times bu will be equal to b times au. It doesn't matter when you are multiplying a and when you are multiplying b, the final resultant will always be same. Okay. So yes, all the properties satisfies in Rn, and hence Rn, or the n-dimensional Euclidean space, is actually a vector space. Okay, and it will actually contain vectors. I told you initially that vector can be any element, but in the Euclidean space actually these elements are actually vectors. Vector is a vector here, okay. So this is how we define it, okay. So in an n-dimensional space, Euclidean space is a vector space. Remember that it is a vector space because it contains all possible vectors. Even if you miss out a single vector, even if you miss out any single vector from it, it will no longer be a vector space. Think about it, okay. Let me give you an example. So is this a vector space? Let's say if I say R3 minus the vector 3, 2, 7. This is a space, okay. This is a set of 3D vectors. So what is it? What does this set represent? R3 we already know. R3 is a set of all possible x, y, z, right? Where x and y and z all are real numbers. From this set, I am removing this particular element. I am removing this particular vector. So from this set, I am removing the vector 3, 2, 7. Now this is also a set, right? From the set, I just removed one vector. So this is all again an infinite set only. But now is this a vector space? Think about it. This will not be a vector space now. The reason being the additive inverse. The additive inverse of minus 3, minus 2, minus 7. This particular element actually exists inside R3. This particular, or let's say we call this entire space as V. This particular element actually exists inside V, right? Because even if you remove this element, this particular vector still exists. But for this particular vector now, the additive inverse does not exist. The additive inverse for this element was what? 3, 2, 7. But this 3, 2, 7 is not present inside the space V. And hence, it is not a vector space now. It is not a vector space now. Now you might think, let's say I create one more vector space in which I remove both of them. If I remove this also and this also, then will it be a vector space? So I will say, like, I am creating another vector space R3 minus, now I am removing two vectors from it, 3, 2, 7 and minus 3, minus 2, minus 7. If I remove both of them, now is it a vector space? So again the answer is no. Why? Because it is now not closed under addition. Even before also it was not closed under addition. The reason being, I can take a vector, let's say 1, 1, 1. This is a vector u which belongs to the set u, and I take a vector v which is the vector 2, 1, 6. This also belongs to the set u, but their addition u plus u vector plus v vector, their addition is what? It is the vector 3, 2, 7. This is the vector 3, 2, 7, and it does not belong to the set u, because from the set u you have already removed 3, 2, 7. So you cannot remove 1 or 2 points like that. Okay, you have to intelligently see. Vector space is like, right now, till now, for the last hour you might be thinking this is a stupid concept, right? Everything is a vector space, but not. Even if you remove 1 or 2 points, it will not be a vector space. But actually there exist, you can actually remove some set of things and it will become a vector space. Okay, we will see that. We will see some more examples. So it is beautiful. And that is why you need to remember all the properties. Here also a few properties were not following, like here also there were a few properties which were not following. And that's why both of these are not vector spaces. But R3 is a vector space. Cool. So let's see more examples. Okay, let's look at the next example. Matrix space. Okay. So set of all m cross n matrices is also a vector space. Okay, it will be hard to digest, but yes. Okay, so any like set of all matrices where order is defined, so all m cross n matrices, okay, is a vector space. So how? Okay, so and also field. So the field can be anything here. You can have any field. Okay, that's magical. So set of matrices is always a vector space, no matter what you take as a field. It should just be a valid field. Okay, so field can be anything. It can be the set of real numbers, set of complex number, or any other field. Okay, So we will try to see it on real numbers, and you can extrapolate it to complex numbers as well. You can have, like in the same matrices, you can have complex numbers as well, and that thing will still hold. So what is the vector set here? The vector set is set of all matrix A, where A is an m cross n matrix with the entries from the field F. Okay, so all the entries inside this matrix will be from the field F. So for example, if we take the field as the set of real numbers, then it will be the set of all possible matrices where each entry inside the matrix is a real number. Okay, so let's take an example. What do we mean by this? So if I take, let's say, the set of all matrices of size, let's say 2 cross 3. Okay, and if we take the field as set of real numbers. Okay, so we are defining the vector space as set of all matrices such that A is a 2 cross 3 matrix. Set of all such 2 cross 3 matrices where each entry is a real number. Okay, because the field was real number here. If it is complex number, then each entry may be a complex number. Okay, like that. So set of all possible 2 cross 3 matrices is also a vector space, because we know that addition is defined on matrices. It's very simple, right? But multiplication isn't. But for a vector space, we don't need to multiply two vectors, right? Only addition should be defined and scalar multiplication should be defined. So it is perfect, right, for matrices. For any 2 cross 3 matrix, I cannot multiply a 2 cross 3 matrix with a 2 cross 3 matrix. That is not allowed, right? I cannot multiply them. That is not even allowed. But that is not even required also. What is required is you should be able to add them. We can add them. And we can also do scalar multiplication, right? Scalar must be from the field. So you can multiply any real number with a 2 cross 3 matrix and you will get another 2 cross 3 matrix with all real entries, right? And similarly, if you add 2 cross 3 matrices, you will get another 2 cross 3 matrix with all real entries. If here we have all real entries, here also we have all real entries, then here also we'll have all real entries, right? So this will also be inside this set. And this matrix will also be inside this set. That is the idea. This actually contains all possible matrices. So all these matrices will be a part of this set, right? And hence closure property is satisfied. Like closure under addition and closure under scalar multiplication is satisfied. You can see that. And even if the field was complex numbers, if here we have all complex numbers, if we add them, we will get complex numbers only, because that is the property of field. If you add any element of a field to any element of a field, you will get an element in the field itself. Right, and same for scalar multiplication, and that is why we can actually have any field. Okay, but we will right now see real numbers only. Cool. So this is the case. Okay, so we will have the closure under addition and closure under scalar multiplication is what we can definitely see here. Cool. Now we want to see the other properties as well. So we can try to do it on 2 cross 3 matrices only for now. So firstly, let us go with, we already know how matrices are added, right? I don't need to write the rules. We already know how we add two matrices. We will just add them component by component, like every element will be added in the same way. And we also know how do we multiply a scalar with a matrix. If you want, I can write it in the shorthand notation here. So let's say, let me define the matrix addition. So if A is a 2 cross 3 matrix and if B is a 2 cross 3 matrix, then their addition C will also be a 2 cross 3 matrix. And how is it defined? Let's say A is A11, A12, A13, A21, A22, A23. And if you add it to another matrix B11, B12, B13, B21, B22, B23, then their addition will be defined as this matrix. It is another 2 cross 3 matrix. Okay, this is a 2 cross 3 matrix. This is a 2 cross 3 matrix, then their addition will also be a 2 cross 3 matrix. A11 plus B11, A12 plus B12, A13 plus B13. Then we will have A21 plus B21, A22 plus B22 and A23 plus B23. Okay, so it will also be 2 cross 3. This is how addition is defined. And similarly, how is scalar multiplication defined? K times any value k from the field R times A. K times A is defined how? So it will be k times the matrix. So it will be just, you will multiply every value with k. So it will be k times a11, k times a12, k times a13, k times a21, k times a22, k times a23. Okay, so right now I'm doing it for 2 cross 3 matrix, but you can actually do it for any m cross n matrix also. And if you see here, how many independent entries these matrices have? They have 6 independent entries, right? 1, 2, 3, 4, 5, 6. They have 6 independent entries from the field. And that is why this vector space is 6 dimensional. This is 6 dimensional. Its dimension will be 6 because it has 6 independent entries. You can have like 6 independent entries from the field inside it, inside one single vector. Now I am calling a matrix as a vector here, because in vector space every element is a vector, right? And inside this vector space the elements are matrices. So matrices are vectors. But you might ask, like, how do I represent a matrix as a vector? Because right now we always represent vectors like this. They have components like this, right, in a single dimension, right? We write it like this. But you can always write any elements in the form of vector. Why? Because even if you have six such elements, you can write them in a vector in a single form as well, right? Like this: a11, a12, a13, a21, a22, a23, like this, right? You can consider it as a vector. So every matrix here can be considered as a 6-dimensional vector in the 6-dimensional space, right? It has 6 different components, okay? And that is why they are called vectors, okay? So every element in the vector space can be thought of as a vector, although it is a matrix here. But you can write it like this and it will become a 6-dimensional vector. Cool? Okay, so this is how addition and scalar multiplication are well defined, and closure is very well defined, right? So if you add 2 vectors or 2 matrices, you will get another matrix which is also a part of this set. And if you multiply it by a scalar, also you will have a matrix which is a part of the same set. So among V, E, C, T, O, R, okay, the closure is satisfied. Closure under addition and closure under scalar multiplication both are satisfied. Now if we look at vector addition, we already know that vector addition is commutative and vector addition is associative. We have already proved it in the matrices. So matrix addition is associative and matrix addition is commutative. We have proved it, and hence vector addition properties are also satisfied. Second is existence. Existence of additive identity. What is the additive identity, or what is the zero vector here? The zero vector here will be the matrix containing all zero values, right? So this will be the zero vector here. This will be the zero vector, right? Or you can call it the additive identity. The additive identity will be the matrix containing all zero values. This 2 cross 3 matrix. This will be the zero vector, okay? So it will be the zero matrix. Zero matrix of size and m cross n, or zero matrix of size 2 cross 3. That is your additive identity, because if you add any vector or any matrix to this matrix, you will get the same matrix back, and hence, and this is also a part of this set, right? All the components are real numbers, and hence this is also a part of this set, and additive identity actually exists. Okay, so zero vector exists inside the set, and hence this is satisfied. And next is additive inverse. Additive inverse for every element also exists, because for any matrix A, the matrix minus A also exists in the same set. It will be just minus A11, minus A12, minus A13, like that. So that is also a set of all real numbers that will also exist in the same set. And hence, yes, additive inverse for every element, for every matrix A is minus A, and that also exists inside the same vector space, okay, M2, 3. Cool. So V is satisfied, E is satisfied, C is satisfied. Then we have the two distributive laws. Again, we have seen this in matrix addition. When we discussed matrix addition and subtraction in module 1, we have seen this property that matrix addition and multiplication and scalar multiplication is distributive. And hence you can write that A plus B times any matrix A will be just A times matrix A plus B times matrix A. You can prove it very easily as well. And also you can say that A times matrix A plus B will be A times matrix A plus A times matrix B. Okay, these two properties also we have proved, the distributive. So T is also satisfied. Then one exists in the field. In the field, one will exist, because in the field always the multiplicative element will exist, right? So here one exists. So if it had been the set of complex number, then we would have taken 1 plus 0 iota. But if it is set of real numbers, then the O or the multiplicative identity is the number 1. 1 exists in the set of real numbers, and if you multiply any matrix by 1, you will get the same matrix back. And hence the scalar multiplicative identity also exists. O is satisfied. And obviously rescaling also works. So you can actually say that AB times any matrix A is A times B times matrix A is equal to B times A times matrix A. If you just see the matrix lecture, we have actually proved all these properties. Okay. And yes, and that is why the set of all matrices, set of all 2 cross 3 matrices is a vector space. And similarly, set of all m cross n matrices is a vector space. So in set of all 2 cross 3 matrices, the dimension is 6. We have 6 independent values which are present. And similarly, in the set of all m cross n matrices, there will be m into n independent values. So it is m into n dimensional. Every vector is in m into n dimensional space. So if you are taking 2 cross 3 matrices, every vector is in 6 dimensional space. And similarly, if you take m cross n matrices, every vector will be in a m into n dimensional space, because you will have m into n independent values. Okay. Cool. So yes, this is why set of all matrices is a valid vector space. Okay. Cool. Now let's look at another example. Next is polynomial space. Even the set of all possible polynomials is also a vector space. Cool. So how is the set of all possible polynomials a vector space? Here note that every polynomial is of degree n. That's why we are writing Pn. So set of all possible polynomials with degree n will be a vector space. Now what is the degree of a polynomial? So if I write a polynomial like this, like 1 minus 2x plus 4x square plus 3x cube. The degree is 3, right? Degree is the highest power for any variable, right? So the degree of this particular polynomial is 3. So this is how we define polynomials. So set of all polynomials with degree n or a fixed degree will also be a vector space. So how? So firstly, let's see, and the field also, here the field can be anything, okay, let me firstly give you an example, then we will discuss about the field. So what if I let's say about set of all possible polynomials with degree 2, set of all possible polynomials of degree 2, and let's say the field is the set of real numbers. So what do we mean by this particular set? What do I mean by this? So it means the set of all polynomials of all 2 degree polynomials with coefficients as real numbers, with coefficients as real numbers, or you can say that every coefficient will belong to the field. So if you are defining it over some other field, then the coefficient can be from that field. So if you are defining it over complex numbers, then the coefficients can be from the complex numbers. Okay. So but right now we will look at the real number set. Okay, let's say the field is on the real number, and hence every coefficient will be a real number. What do we mean by coefficient? This is how a polynomial is defined. You can say it like this: a naught. How does a 2 degree polynomial look like? A generic 2 degree polynomial looks like a naught plus a1x plus a2x square. This is how a general 2 degree polynomial looks like. Okay, so it is just like the set of all these polynomials such that a0, a1 and a2, these are coefficients. They belong to real number. They are all real numbers. Okay, for example, like if you take all of them as 0, 0, 0, you will just get 0 plus 0x plus 0x square. So you will just get the polynomial as 0. And if you take them 1, 1, 1, you will get 1 plus x square. This is a polynomial. And if you take them like let's say minus 3 and plus 5 and then 0, then you will get this polynomial. And if you take let's say 7 and then 0 and then you will take 3, let's say, so 7 plus 3x square, this is also one polynomial. And if you take first coefficient as 0, then you can get, let's say, x plus x square. This is another polynomial, and so on. Right? You will have a set containing like polynomials like these. You can have different coefficients, and all such coefficients are real numbers. So how many different values, how many different coefficients do we have? How many independent values do we have in this space? Okay, let's say for now it is a space. So how many independent values do we have? A0, A1 and A2. We have 3 independent values, and all these 3 independent values can be from the field. So that is why it is a 3-dimensional vector space. It has 3 independent values, and every such polynomial can be represented using a 3-dimensional vector. So this particular can be represented as the 3 coefficients are 0, 0, 0. Here the 3 coefficients are 1, 1, 1. Here the 3 coefficients are -3, 5 and 0. Here the 3 coefficients of A0, A1 and A2 are 7, 0 and 3. Here it is 0, 1, 1 and so on, right? So every such polynomial can be represented in a 3-dimensional vector, and that is why every vector will be in 3-dimensional space, and that is why this vector space is a 3-dimensional vector space. Okay, although the degree is 2, but we will have a constant term also, right? Because of this constant term we will have it, the degree of this the dimension of this vector space is 3. Okay, cool. So this is how the vector space is defined. Now addition is very simple. You can add 2 polynomials. You just have to add coefficients, just like vector addition. So if you want to add this polynomial, let's say if you want to add this polynomial with this polynomial, you will just add them. So -1 plus 3 will become -2, then x plus 5x will become 6x, and then x square and 0x square will become x square. So essentially you are just adding these 2 vectors, right? So this is nothing but -2 comma 6 comma 1. You are just adding these 2 vectors and getting the polynomial addition also. Same happens with the scalar multiplication. Let's say you want to multiply this particular polynomial with a scalar 3, then you will get 21 plus 9x square, which is nothing but 21 comma 0 comma 9. So you are just multiplying, let's say if I multiply this by 3, so I'm just multiplying this particular vector by 3. So every property will be just like vector addition and vector multiplication only, right? And that is why, because we already know R3, because like this now becomes R3. If I just convert the set of all polynomials to set of all vectors, there is a 1-to-1 mapping, right? Every polynomial will have a unique 3-dimensional vector, every 3-dimensional vector will have a unique polynomial. And we already know R3 is a vector space in R, and that is why we can say that set of all polynomials is also a vector space in R. But yeah, you can check, right? Like all the properties will be satisfied. Addition of 2 polynomials will be another polynomial, and it will also be a, like if you add two degree polynomials, you will again get a 2-degree polynomial, right? And that will also be a part of this set. And if you multiply any polynomial by a constant, then you will get another polynomial which is also in the same set. And what is the additive identity here? The additive identity is the 0 polynomial. It is just the 0 polynomial, or this vector 0 comma 0 comma 0. This polynomial 0 plus 0x plus 0x square. 0 polynomial is actually the additive identity, because if you add it to any vector or any polynomial, you will get the same polynomial back. And additive inverses also exist. For example, for 7 plus 3x square, the additive inverse will be -7 minus 3x square. If you add these two, you will get the 0 polynomial, right? So for vector also, you just have to multiply it with -1. Cool. So additive inverses exist, distributive law holds, commutative, associative, all laws will hold, and also the scalar multiplication identity, which is 1, is present in the field, and hence it is also a vector space. I hope this makes sense. Okay, and this we proved for degree 2. Actually you can prove it for any degree n. Set of all polynomials with degree n, you can have n here, then you will have n plus 1 components, a0 plus a1x plus a2x square and so on, plus an x to the power n. So you will have n plus 1 components. It will be an n plus 1 dimensional vector space, because you will have n plus 1 different unique components or independent components, and that will also be a vector space, right? So we can extrapolate this, and we can say that any polynomial space with degree n, okay, so it is defined here, right? So it is like set of all polynomials of x, where px is a0 plus a1x plus a2x square and so on, an x to the power n. So how many different values we have? a0, a1, a2 and so on an. So we have n plus 1 different values. So it is an n plus 1 dimensional vector space, and every coefficient is in the field f. So this field can be real number, complex number, anything, but the same properties will hold true. Okay. So set of all polynomials is also a vector space. Let's look at more examples. Okay, next we have a very interesting example, set of all complex numbers. So set of all complex numbers is also a vector space, and it is a vector space over set of all complex numbers also, and it is a vector space over the set of all real numbers also. Okay. So the field can be the set of all complex numbers or the set of all real numbers, and it will be two different vector spaces. How? Let's see. So firstly, let's see based on set of all real numbers. So what is the set of all complex numbers? I can write it like this, right? It is the set of all x plus y iota, where x and y both are real numbers. So here I am defining this particular set of all complex numbers. This is how any complex number will be defined, right? It has a real part and an imaginary part. The real part is x and the imaginary part is y, and they are both real numbers. And I am just multiplying y with iota to make it imaginary. And this particular set of complex number is defined over the field R. It is defined over the set of all real numbers. So here I have two components. Here I can say that, like, see here, like, what are the complex number? I can say 0 plus 0 iota, which is just 0. Or we can have 1 plus iota. Or we can have minus 1 plus 7 iota. Or we can just have 3 plus 0 iota. Or we can have, let's say, 0 plus 10 iota. And so on. Right? So this is how, like, all the complex numbers will look like. And you can actually pull out the real part and imaginary part differently, and you can write it as vectors as well, like in two-dimensional space. I can write it as the vector 0, 0, and I can write this as the vector 1, 1. I can write it this one as the vector minus 1, 7. I can write this one as the vector 3, 0. I can write this one as the vector 0, 10, and so on. So actually there is a one-to-one mapping between the set of all complex numbers and the set of all two-dimensional vectors R2, right? There is a one-to-one mapping. For every unique vector in R2, you will have a unique complex number, and for a unique complex number, you will have a unique vector R2. And we already know R2 is a vector space in R, right? And hence the set of all complex numbers is also a vector space on R, okay, on the set of all real numbers, where the field is the set of all real numbers. So here I am writing a complex number in this notation. So I can actually, like, write any complex number, I can draw it on a two-dimensional space. I can draw any complex number on a two-dimensional space. I will have the real part here and I will have the imaginary part here. And any complex number can be defined as a vector, right? And it will be a vector space because, yeah, you can add two complex number and you will get another complex number, and you can add, like, multiply it with a scalar, you will get another complex number which will also be a part of this. And you will have additive inverses, you will have like, all the properties will satisfy. You can check that, okay? All the properties in vector will be satisfied. So this is the one way of defining it. But here we are saying this is the set of all complex number and the field is the set of real numbers, and we have two independent entries here. Right, we have two independent entries, which means every vector inside the complex number set, every element inside the complex number set is a two-dimensional vector, and hence if we represent it over the set of real numbers, then the set of complex number is a two-dimensional vector space. It is a two-dimensional vector space in this notation, because every vector is two-dimensional. It has two independent entries, right? So it is a two-dimensional vector space. But another way of writing a complex number can be set of all complex number is C, where C belongs to the set of complex numbers. Just C, right? So it's like just the first example that we saw, set of all real numbers on set of all real numbers. Same thing we can do, set of all complex numbers on set of all complex numbers, because set of all complex numbers is a field also, right? So what will happen here, we are just saying that every element will be a complex number, and we are taking it from the field which contains all possible complex numbers. So here, if you notice carefully, here we don't have two components. right? Here we are not taking two components from the field. Here we are taking a single element from the field. So this one now becomes a one-dimensional vector space. If you represent it over the set of all complex numbers, so if you write the set of all complex number, the vector space over the set of all complex numbers, the field is complex number, then it will be a one-dimensional space, because you are just taking the elements directly from this field. But here you are taking two elements from the field and then creating a complex number. So here it was a two-dimensional vector space, but here it is a one-dimensional vector space. In any case, it is a vector space. Why is it a complex vector space here? See, you will not be able to draw it like that. You will not be able to draw it like that, because here set of all vectors, the possible values is like apple, oranges, bananas, right? Apple, oranges, bananas you cannot plot, right? Here the elements will be like 0 plus 0 iota, this is one particular element, it does not have two components, and then 1 minus iota, this is one particular element. So I cannot draw them on a Euclidean space like this. I need some imaginary space which contains all possible complex number on a number line. We cannot have that, right? So it is not possible to draw it, but yeah, I hope you get the idea, right? This is one particular element, this is one particular element, consider this as pen, apple, banana, and so on. And here also we have all the properties satisfied. What is the additive identity? The additive identity is this particular vector, 0 plus 0 iota, because you add it to any other complex number, you will get the same complex number back, right? And we also have a scalar multiplicative identity. The scalar multiplicative identity inside this field is the element 1 plus 0 iota, right? Because if you multiply any vector with this scalar, right now you are considering this entire complex number as a scalar. Complex number can also be a scalar, right? You are just multiplying any vector with a complex number here. So if you multiply any complex number with 1 plus 0 iota, you will get the same complex number back. And hence the scalar multiplicative identity, or the number 1 will be 1 plus 0 iota now, okay? And this will be the additive identity. And additive inverse is very simple. For any number, for any complex number C, the additive inverse will be minus of C, okay? You just multiply it with minus 1. And all the properties will satisfy, because all the properties satisfy on a field. This will also be a vector space. But you need to see the difference, okay? Here we are taking two components out, and hence we are representing it in a 2D vector space. Here we are just taking all of them as single elements, and the field itself contained complex numbers. So even if you don't understand this part, it's okay. It's not highly relevant to the exam, but understand that the concept itself, the set of all possible complex numbers, is a vector space. And the dimension of the vector space actually depends on what field you are taking, okay? If you are taking real numbers, it is two-dimensional vector space. If you are taking the field as complex numbers, it is a one-dimensional vector space. Cool. So here it is written, the same thing is written. If you are representing a set of all complex number as a vector space over C, if the field is the set of all complex numbers, then the vector set is C itself. And if you are representing, and it is a one-dimensional vector space here, and it is a two-dimensional vector space here. If you are representing it over R, or the set of all real numbers, here the set will look like this, A plus B iota, where A and B both belong to the field or the set of real numbers. Cool. So these were a few examples of vector spaces. Okay, let's see a few more examples. So these are non-examples actually. These are not vector spaces. So let's try to see what they are. First is R plus. So the set R plus means set of all positive real numbers. Okay, it is set of all positive real numbers under addition and multiplication. Okay, so what all properties will this satisfy? Set of all positive real numbers over R only. Let's say the field is the set of all real numbers only. Okay, cool. So set of all positive real numbers, which means it will start from 0, then 0.001 and so on. Okay, it will start from, it will actually not start from 0, even 0 is not included. Even 0 is not included. It will contain the set of all only positive real numbers. Okay, so 0 will not be there and all the negative real numbers will not be there. So is this a vector space? So on number line we can represent it like this, because it is a one-dimensional space. 0 is not included, and we are taking all possible numbers in the positive x direction like this. We are not taking any numbers from the negative x direction. So what will happen? It is not a vector space. Why? If I look at the properties, first is V, which means vector addition being commutative and vector addition being commutative and associative. Vector addition, so addition of two real numbers will be commutative, right? Addition of two real numbers is commutative and it is associative. These properties are satisfied. But E, does there exist an additive identity? Additive identity was the element 0, but 0 is not included in the part in the positive real numbers, and hence additive identity does not exist. Additive identity does not exist. And even additive inverses also do not exist, right? Because for number 5 the additive inverse must be -5 to get the 0, right? -5 also does not exist, so additive inverses also do not exist, and hence like even in existence we failed. But let us check all the properties. Closure, so does the addition of two positive real numbers also a positive real number? If I add 3 and 2, I'll get 5. So addition of any two positive real numbers will give you another positive real number, and hence it is closed under addition. And is it closed under scalar multiplication? If I multiply it with a negative number, because see, this particular set is defined over R. Let's say it is defined over the field R, or the set of all real numbers. So it is not closed under scalar multiplication. Why? Because if I multiply any positive real number with a negative scalar, let's say if I multiply 3 with -3, I'll get -9, but -9 is not part of the vector set, and hence it is not closed under scalar multiplication. C is also failing. Next is the distributive laws. The two distributive laws will hold. Okay, the two distributive laws will hold true. They will hold true anyway, okay? And actually, like here also the negative numbers might cause a trouble, right? Because like what are the distributive laws? We have a plus b times any vector u should be equal to au plus bu. Okay, but yeah, this will hold true, right? This will hold true, but au but plus bu might not be a part of the vector set. Okay, so again, like we cannot say that the distributive laws hold true here as well. Cool. And then the existence of 1 actually exists as a part of real number set. That is okay. So 1 is satisfied, and then rescaling is also satisfied. Cool. But yeah, there are a lot of properties failing, and hence this is not a vector space. Okay, you cannot just have all positive numbers. And notice the fact that any vector space will always have the origin, right? This is the most important property. This is the first property you should always check. Additive identity exists or not, which means 0 should exist. 0 will be part of any vector space because additive identity must exist. Okay, and if 0 exists, then only additive inverses will exist, right? Because you'll have to add them and get the 0 vector. Cool. Next is this one, set of all possible x comma y in R2. So it is defined over R2. Basically it is defined over R. Okay, the field is R. So set of all possible x, y such that x plus y is equal to 1. X plus y is equal to 1. What does it mean? They are saying they are not taking the entire space. They are not taking the entire, like, let me. Okay, let's firstly have the same set. Set of all possible x comma y such that x plus y is equal to 1. Okay, this is the vector space given to us. Set of all x comma y such that x plus y is equal to 1, and x and y both are real numbers. Okay, and we are defining it over the set of all real numbers. The field is R. Cool. So this is the vector space. We want to check it is a vector space or not. So if I try to draw it, what are all the points we are taking? X plus y is equal to 1. Okay, which means x is equal to 1 and y is equal to 0 is there. And x is equal to 0 and y is equal to 1 is there, and we are actually taking all the points on this line. We are taking all the points on this line. So I'm not taking the entire space, I'm just taking this particular line. Okay, so one thing is for sure, you can see that origin is not there in this space, so additive identity does not exist. See 0 comma 0 is not present inside this particular vector space, and hence additive identity won't exist, which means you cannot have a particular vector inside this which when added to every vector will give you the same vector back, because that has to be 0 comma 0, and 0 comma 0 is not part of this because 0 plus 0 is not equal to 1, and hence additive identity does not exist, and hence it is not a vector space. And even if you had some but let's take another example. Okay, this is not a vector space, this we figured out. If I take another vector space, let's say U, which is set of all possible x comma y such that x plus y is equal to 0. Let's say x plus y is equal to 0 and x and y are real numbers over R. Okay, now we are taking x plus y is equal to 0, which means 0 comma 0 will be there. So let us draw it using some other color, green color. So 0 comma 0 will be there, then minus 1 comma plus 1 will be there. Okay, minus 1 comma plus 1, which means somewhere here, and then 1 comma minus 1 will be there, which means here. So it will be line parallel to this line. Okay, like this. Okay, I'm not very good at drawings, but I hope you understand this line. Okay, this is x plus y is equal to 0, and the previous one was x plus y is equal to 1. Okay, cool. So is this a vector space? Is U a valid vector space? So this is passing through origin. This is passing through origin. So 0 comma 0 is there. Additive identity exists. So let's try to see our properties. We are just taking all such points on this particular line. Okay, we are just taking all points on this line. So this space does not contain all possible points. It only contains all possible vectors which lie on this particular line. Okay, cool. So what will happen? Firstly, let's start with addition. Addition is well defined. Scalar multiplication is well defined. The definition is clear. But now we want to check the properties. So first property is V. So V is vector addition is commutative or not. A plus B will be equal to B plus A. Whatever A and B are, A plus B will be equal to B plus A. Vector addition is commutative and it will be associative as well. So V is satisfied. Next is existence. Existence of identity, additive identity. Existence of additive identity. 0 comma 0 exists. So 0 comma 0 exists and additive identity exists, which means you add 0 comma 0 is actually present inside this set, and if you add it to any vector, you will get the same vector back. Additive identity exists. Now we want to check additive inverses. For every element, does the additive inverse exist? Which means if x comma y belongs to this vector space, does minus x comma minus y, because minus x comma minus y will be the additive inverse of x comma y, right? Because if you add them you will get 0 comma 0. Is this also a part of the vector space? So for every possible x comma y, so let's say for every possible x comma y, if I take any possible value, let's say minus 1 comma 1, okay, this particular point. For minus 1 comma 1, if minus 1 comma 1 is in the vector space, is 1 comma minus 1 also in the vector space? Yes, right? So for every possible point, its additive inverse will be here on the same line. For every possible point, that its additive inverse will be also on the same line, because if you add them up, you will get the 0 vector, right? And hence it is satisfied. Even the additive inverse for every possible point or every possible vector also exists, and it also is a part of the same vector space, vector set. So this property is also satisfied, right? So E is satisfied. Next is C, closure. Closure under addition. So this is very important again, we have to prove it. So if x1 comma y1, and actually you can prove this one also mathematically, because if x plus y is 0, if x plus y is 0, then minus x minus y will also be 0. It is just minus of x plus y, which means it is just minus of 0, which is 0 only. And if x comma y exists, minus x comma minus y also exists. We just took it from the graph, but also you can see it mathematically, okay? Okay, now let's see closure under addition. So if x1 comma y1 exists, so if x1 comma y1 is belonging to the set U, and let's say this is the vector A, and there is a vector B which is x2 comma y2, which is also belonging to the set U, then their addition should also be a part of the set U. This is what closure under addition means, right? Which means if x1 comma y1 is in set 1, is in this set, it means that x1 plus y1 has to be 0. And if x2 comma y2 is in the set, which means x2 plus y2 also has to be 0. Then only these 2 points can be a part of this particular line. And what is vector A plus B? Vector A plus vector B will be x1 plus x2, y1 plus y2, right? And their sum is also 0, right? x1 plus x2 plus y1 plus y2 will be what? x1 plus y1 is 0, x2 plus y2 is 0. This will also be 0, which means if vector A is inside the set and vector B is inside the set, then their sum is also inside the set, which means it is closed under addition as well. And you can see it on the graph as well. If you have any point on the line, and if you have another point on the line, then their addition will also be on the same line, right? It will always lie on the same line. Okay, so yes, it is closed under addition, and actually it is closed under scalar multiplication also. Why? Because if x comma y is inside the set, if any x comma y is inside U, then k times x comma y, this is scalar multiplication, right, will be what? It will be kx comma ky. So if x plus y is 0, then kx plus ky will also be 0. It is just k times x plus y, which is also 0. So you actually scale any point, you will be lying on the same line only, right? If you scale this point, you will land here. If you scale, like, you will be essentially on the same line, and hence it is closed under scalar multiplication as well. Okay, so magically we are actually seeing a vector space now which is not containing all possible points. It is just a single line, and a line can be a vector space as well. Okay, so cool, it is closed under addition, it is closed under scalar multiplication. Now what about T? The two distributive laws. The distributive laws will hold true. They are like pretty much like they are the properties of addition and multiplication. So distributive laws will hold true, and the scalar multiplicative identity is also there. One is present inside the field, one is present in this field, and if you want to multiply one with any of the vectors, you will get the same vector back. Okay, so one is also true. And then rescaling will also work fine. It doesn't matter, like if you scale it once, if you scale this point by 2 times, you'll get here. If you scale by another 2 times, you'll land here, and if you scale it by 4 times, you'll land at the same space. And hence actually VECTOR, all the 10 properties are satisfying for this particular space, and hence U is a vector space. It is a vector space. V was not a vector space because it was not passing through the origin. So later we will try to see any line which passes through origin in a 2D space will be a vector space or not. We will try to see it later. Okay, when we see subspaces in the next lecture, we will try to see this concept. Okay, this is actually a subspace. This is actually a subspace of R2 because it is a subset of R2. It is a subset of points, right? So we will understand the concept of subspace in the next lecture. But I hope you understood that this is actually a vector space because it satisfies all the properties. Even the set, it is a restricted set of points, but it contains origin, and actually it contains all possible, like all the rules are satisfying, which means you add 2 vectors, you'll get land on the same line. You multiply any vector to any by any scalar, you'll land on the same line, and so on. Okay, cool. But essentially in this example, this is not a vector space. Cool. Next is R2 with scalar multiplication defined like this. Okay, so they changed the definition of scalar multiplication. They changed the definition of scalar multiplication. So let's look at this. So R2 with scalar multiplication defined as k times x comma y is kx comma 0. Okay. So R2 with scalar multiplication definition itself is changed, is defined as k times x comma y is equal to kx comma 0. This is how they are defining it. Okay, so the set remains same. R2 is the set which is like set of all possible x comma y such that x and y both are real numbers, and we are defining it over R. We are defining it over R. This is the vector space given. The original R2, we know that R2 is a vector space, but there the definition of scalar multiplication is different, right? So they did not change the definition of vector addition. Addition still remains the same, okay, I believe. So what will happen for any 2 vectors? Let's say u vector is x1 comma y1 and any vector v which is x2 comma y2, then the vector u plus v is still same. The vector u plus v will be x1 plus x2 comma y1 plus y2. That is same. But they change the definition of scalar multiplication. So scalar belongs to the field. Field is the set of real numbers. Okay. So scalar times this vector will now be different. It will be k times x1 and the y component automatically becomes 0 whenever you multiply it by a scalar, the y component becomes 0. Okay. So this is the vector, like this is the definition of scalar multiplication given to us, and now we need to deduce it is a vector space or not. Okay, so let's look at the properties one by one. Cool. So what are the properties? Vector addition is the vector addition commutative and the vector addition associative, right? So V is for vector addition being commutative and associative. So vector addition definition did not change. Vector addition is still the same. You add them still the same. So it will be commutative, it will be associative. It did not change at all. Next is existence. Existence of additive inverse. Existence of additive inverse. So 0, 0 is still a part of this vector. 0, 0 is still a part of the vector, and hence if you add any vector to 0, 0, you will get the same vector back. And hence additive inverse exists, and it is the vector 0, 0. Okay, and additive inverse for any vector. So if you have a vector u, which is x comma y, then the additive inverse will be minus x comma minus y, and addition definition is still same, and you will get the 0 vector back. And if you have x comma y inside this vector space, then minus x comma minus y will also be in the same set, and hence additive inverse for every element also exists. Okay, so existence is satisfied. Next is closure over addition. Firstly, let's say closure over addition, which means if you have any vector u and any vector v, is their addition actually present inside the same set. So the like u plus v will be what, like it will be x1 plus x2 y1 plus y2. It is actually like they are both real numbers. X1 plus x2 and y1 plus y2, they are both real numbers, and this will also be part of the same set, and hence it is closed under addition. And closed under scalar multiplication means what? K times u. K times u. K times u will be what? K times u will be k times x1 comma 0. So this will still be part of the same vector space, right? This vector is actually present inside the vector space because k times x1 and 0 both are real numbers. And still like k times x1 comma 0 will be a part of the same vector space, and hence it is closed under scalar multiplication as well. So far all the properties are there. Next is the two distributive laws. So I don't think distributive laws will change. The distributive laws will hold true. Again, like a times b times a times u plus v. A times vector u plus vector v will be what? Vector u plus vector v is this vector, and if you multiply it with k or a, you will get a times x1 plus a times x2 comma 0. Okay. Which is it equal to a times u plus a times v? It is actually equal to a times u plus a times v, right? And hence this distributive law holds true as well. And the next distributive law is a plus b times u should be equal to a times u plus b times u. Does this distributive law hold true? So a plus b times u will be what? A plus b times x1 comma 0. It is a plus b times x1 comma 0, and they are both same. This will also be a plus b times x1 comma 0. So the distributive law holds true. Both the distributive law holds true, the two distributive laws. Okay. Now next is O. O is what? O is the existence of the scalar multiplication identity. The existence of scalar multiplication identity, which means 1. So 1 is a part of the field. 1 is the part of the field. But we need to ensure one more thing, right? That 1 times any vector must give you the same vector back. 1 times any vector must give you the same vector back. But like if you do 1 times the vector u, 1 times the vector u, what will happen? You will have 1 times x1 comma y1. So you will get 1 times x1 comma 0. So the definition of multiplication changed, and hence 1 times x1 comma y1 will be 1 times x1 comma 0. So it will be x1 comma 0. we do not get the same vector back. So actually we don't have any scalar multiplication identity in the field. You cannot have a single number inside the field when if you multiply all the vectors by that number, you will get the same vector back. No, right? Because you are getting a different vector back because the y coordinate becomes 0. So this property is actually failing, right? Crazy. Like all the other properties are satisfying, but this property is failing. Okay. So existence of scalar multiplication identity is not present. Okay, that is not present inside this vector space, and hence this is not a vector space. And actually R will also satisfy, like, because rescaling will work, because if you multiply it with A and then B, it doesn't matter, you will have AB times x1 comma 0. So rescaling will work, but the only property which is not satisfied by this particular vector set is the existence of scalar multiplication identity, and hence it is not a vector space. Okay, it was so close, but it did not crack. Okay, so this is not a vector space. Okay, so we can say that this is also not a vector space. Cool. So generally speaking, what is happening, like for vector spaces? We saw a vector space example, right? Like a line passing through origin. We saw x plus y is equal to 0 was a vector space. This was a vector space. So why did this happen? So if you look at the properties, let's try to summarize them. What is actually happening? So we have existence of 0 vector. This is a very important property. Okay, like I am telling you how to quickly check a particular space is a vector space or not. Existence of 0 vector, it is one of the most important properties. 0 vector must be present. Okay, so any, like if you are working on R2, if you are working in R2, then it must be passing through origin. Whatever line or whatever is given to you, it must be passing through origin, right? So 0 vector must be present. And if you look at the properties of closure, closure under addition and closure under scalar multiplication, which means, like, what does these two property tell us? So closure under addition tells us that vector u plus vector v must also be a part of the same vector space. If u is a part of a vector space and v is a part of a vector space, then u plus v should also be part of a vector space, which means if you add any two vectors inside the vector space, their sum should be a part of the vector space itself. And scalar multiplication tells us that k times u should also be the part of the vector space. If u is a part of a vector space, then k times u should also be part of vector space, which means you multiply any vector by any vector by any number, which means, like, if I take any number, any vector, if I multiply it by any number, I'll get somewhere here. Like essentially I'm getting on the same line here. Or even if you work on R2, so let's say I have a vector here, okay, and I have another vector here, then their addition will be what? Their addition will be somewhere here, right? But even there is scalar multiplication. So what will happen? Like the scalar multiplication of this vector and the scalar multiplication of this vector, they must also be a part of the same vector space, and their addition should also be a part of the same vector space. So essentially we can say that k times u should also be part of the same vector space, and k times v should also be part of the same vector space, and their addition should also be part of the same vector space, which means you take any two vectors, and even you can have k1 here and k2 here, right? K1 times u vector plus k2 times v vector. This thing should be a part of the same vector space, which means any linear combination of two vectors you take in the same vector space, this is what is called a linear combination. We will see this particular definition, like the particular point, what is linear combination, in detail in the coming lectures. But this is what is linear combination. Linear combination means what? You take a vector, you multiply it with something, you take another vector, multiply it with something else, you add them, and this is a linear combination, right? Something times a vector plus something times another vector. So this is the linear combination of these two vectors. And any linear combination must be a part of the same vector space, then only it will be a vector space. Okay, so this is very important property, and we will reiterate on this property later. Okay, like why is this property very useful, what is actually linear combination, and how it works with spaces. Cool. So let's see some more examples on vector spaces. Before that, we have some derived properties. See, these we have already seen 10 axioms, right? So those particular 10 axioms, if any vector set satisfies, then it will be a vector space. But these are additional properties. These are additional properties which you can derive from those 10 properties. So any vector space will satisfy these properties as well. Okay, so let's look at these derived properties one by one. Okay, let's see the derived properties one by one. So first is zero vector is unique. We know that every vector space, so these are all the properties of vector spaces. Okay, they are properties of vector spaces. So we are assuming we are talking about vector spaces for now. Okay, so zero vector in any vector space will always be unique. So I told you, like, vector space can have any type of elements, and zero vector can be any element. It's not like zero vector can be a matrix. You are thinking, like, you might start having a bias that vector is a vector, but no, like here zero vector can be any element, right? And it just has a property that if you add it to any of the vector, you will get the same vector back. So for any vector space, always there will be only a single zero vector. You cannot have two zero vectors. So how will we prove it? The proofs of these properties are not very straightforward, but I'll try to give the proofs to you. Okay, so the first property that we have is zero vector is unique. So how do we prove it? So let's say we have a vector space V, okay, and it has, let's say, two zero vectors. Let's say it has two zero vectors. First is this, and second is something else. Let's say zero vector prime. Let's say both are zero vectors for V, for this vector space. Okay, so let's say like we are assuming this. Okay, then what will happen? They will both satisfy the property of zero vectors, which means, like, let's take the zero vector. Okay, then can I write the zero vector as zero vector plus zero vector? Or any zero vector can be written as zero vector plus zero vector. Why? Because zero vector has this property. If you add it to any vector, you will get the zero vector back, right? So I can write the zero vector as zero vector plus zero vector, and also the zero dash vector. The zero dash vector also is a zero vector, and hence I can write it as zero vector plus zero dash vector as well. Because if you add zero dash vector to any vector, then also you will get the zero vector back, right? And now because of this property, zero vector plus zero dash vector will also be the zero dash vector. Think about it. See why? Because zero vector is the zero vector, right? It means that you add it to any vector, you will get the zero vector. And also zero dash vector is also zero vector, which means you add this to any vector also, then also you will get the zero vector back. And if you add zero vector to any vector, you will get the zero vector back, and zero vector, like zero dash, is also a zero vector. And that is why, because of this entire sequence, we can say that zero vector must be equal to the zero dash vector. Okay, you might think like this is a very meaningless proof, but trust me, this is the only way you can prove that actually for any vector space, zero vector will always be unique. Okay, if you assume there are two of them, they must be equal, and hence they will always be unique. Okay, so this is proved. Now the second property is additive inverses are also unique. Okay, so for any element in a vector space, it cannot have two additive inverses. There will only be a single additive inverse. Okay, so second property is additive inverses are unique. Additive inverse for all elements are unique. Okay, so how will you prove this? Again, let's say for a particular vector u, there exist two additive inverses. So let's assume there are two additive inverses for the vector u. Let's say v vector and v prime vector. Both are additive inverse. Both are additive inverse of u vector. Then it will mean that u vector plus v vector will also be 0 vector, right? And this is the 0 vector for the space. Okay, so because like that's what additive inverse means. If you add it to the original vector, you will get the 0 vector. And also the u vector plus v dash vector, this will also be 0 vector. Okay. And from both these properties we can figure out that v vector and v dash vector must be the same. Why? Okay, let's try to write v vector. Okay, so I can write v vector as v vector plus 0 vector, right? Because of the additive identity property. Because 0 vector is additive identity, this should hold true. Then we can write 0 vector as u vector plus v dash vector. We can write it as u vector plus v dash vector, right? This is what 0 vector is because of this. And now since addition is associative property, okay, we can write it as v vector plus u vector plus v dash vector. Okay, and now since addition is commutative also, because of commutative property, we can write this sum as u vector plus v vector. Okay, u vector plus v vector plus v dash vector, and u vector plus v vector is 0 vector, so this must be 0 vector plus v vector, and again we will apply the additive identity property, and this v dash, this will just become v dash vector, and hence v vector must be all equal to the v dash vector. So if there are two additive inverses, they must be equal, and hence we have just proved that for any element the additive inverse will also be unique. Again, like, proofs are not required for you in exam, but I'm just giving it for you for your reference, and this is how you should prove, because they are vectors. We cannot just directly apply our intuition on them, right? So this is how we'll have to prove it. So additive inverse for all elements in a vector space will also be unique. Cool. Let's move to the next property. 0 times any vector will be the 0 vector. Here this 0 is a scalar and this 0 is a vector. So 0 times any vector will be the 0 vector. Cool. So notice here that this 0 is a scalar. Okay, this is from the field. This 0 is from the field, it is a scalar, and this 0 is a vector, this is from the vector set itself. Okay, and that we are doing a scalar multiplication here. So for any field, if you have a number 0, I can write it as 0 plus 0 as well, right? Because this is the number 0. For any field, the number 0 is what? It is the additive identity of the field. So I can write it as 0 plus 0. So okay, we can write it this way. So 0 times v vector is nothing but 0 plus 0 times the v vector, which is nothing but 0 times v vector plus 0 times v vector. Okay. Now what will happen? So 0 times so 0 times v vector will have an additive inverse as well. See, this is a scalar multiplication. It must, so the point is 0 times v vector must be part of the vector space, and its additive inverse must also be a part of the vector space. Let's say its additive inverse is any vector p vector. Let's say p is the additive inverse of whatever, like is the additive inverse of, because I cannot just assume it is as 0 vector. That's what I want to prove. Okay, so let's say p vector is the additive inverse of 0 times v vector. Okay, and if I add it on both sides, then what will happen? I'll get 0 times v vector plus p vector will be equal to 0 times v vector plus 0 times v vector plus p vector. And now because of the property of additive inverse, this entire thing will be nothing but the 0 vector, right? Because if you add any vector with its additive inverse, you will get the 0 vector. And here also this will become the 0 vector. So you will get 0 times v vector plus 0 vector. And if you add any vector with the 0 vector, you will get the same vector back because of the property of additive identity. So we will get 0 times v vector. So we just proved that 0 times v vector is nothing but 0 vector. Okay. So you multiply any vector with the number 0 or the 0 of the field, then you will get the 0 vector as the answer. Okay. Cool. Let's look at the next property. Next property is also quite similar. It is like any scalar times the 0 vector will be the 0 vector only. Okay. Any scalar from the field you take, you multiply it with the 0 vector. It is scalar multiplication again. You will get the 0 vector again. Okay. Here we have 0 vector 2 times. Okay. So let's try to prove it in a similar way. So the property is a times 0 vector is 0 vector. How will you prove it? Let's try to prove it in a similar way. Okay. So a times 0 vector will be what? It will be a times 0 vector plus 0 vector, because 0 vector is additive identity. This should hold true. And we can write it as a times 0 vector plus a times 0 vector because of distributive property. And if we add the additive inverse of a times 0 vector on both sides, we will get 0 vector here and we will get a times 0 vector here, because if we add additive inverse on both sides, this will go away and this will go away. So this is what we will get. Okay. So you multiply any, if you multiply the 0 vector by any scalar, you will get the 0 vector only. Cool. So these two properties will also hold true for any vector space. Cool. Let's move to the next property. Minus 1 times any vector is minus of v vector. Okay. So the property is minus 1 times any vector will be minus of the same vector. Okay. So what does this property mean? If you multiply the scalar minus 1 from the field, and if you multiply it with any vector, then you will get the additive inverse of the vector. See, minus of v vector is nothing but the additive inverse of the vector. Okay. So if you multiply the scalar minus 1 from the field to any vector, we will get the additive inverse of that vector. Okay, that's what we have been using as well. Okay, so far. So why will this happen? So let's try to prove it. So what is v vector? Let's say I want to compute v vector plus minus 1 times v vector. Let's say I want to compute this quantity. Okay. So v vector can be written as 1 times v vector plus minus 1 times v vector. Okay, I can write v vector as 1 times v vector, right? Because 1 is the multiplicative identity. Okay, and now because of distributive law, we can write it as 1 plus minus 1 times v vector. Now minus 1 is what? It is the additive inverse of 1 in the field. Minus 1 is the additive inverse of 1 in the field, and hence 1 plus minus 1 has to be 0. So it will become 0 times v vector, and we already know that 0 times v vector is nothing but the 0 vector. So we just figured out that v vector plus minus 1 times v vector is the 0 vector. It means that we already know that additive inverse of any vector is unique. Additive inverse of any vector is unique. It means that we added this vector to v vector and we got the 0 vector, which means this must be the additive inverse. This must be the additive inverse of v vector. And if this is the additive inverse of v vector, it means that this is nothing but minus of v vector. Okay, and hence this will be proved. Okay, very simple. Cool. Okay, they are like all these derived properties are very intuitive. Okay, so don't worry about them too much. If you understand the proof, it's good. Cool. Next is u vector plus w vector is equal to v plus w. If u plus w is equal to v plus w, then u and v vectors must be same. Okay. So the property is, if u vector plus w vector is equal to v vector plus w vector, then u vector and v vector are same. Okay. So how do we prove it? It is very simple. We can add the additive inverse of w on both sides. So let's say that p vector is additive inverse of w vector. Then we can add it on both sides we will get u vector plus w vector plus p vector, because it is anyways associative as well. You can add the bracket anywhere you want, and it will become v vector plus w vector plus p vector. Now w vector plus p vector is what? It is 0 vector, because p vector is the additive inverse of w vector, and hence u plus 0 vector will be equal to v plus 0 vector, and if you add any vector with the 0 vector, you will get the same vector back, property of additive identity, which means that u vector and v vector must be same. Very simple proof. Okay, so this is how you can prove this one as well. Cool. Now we have one more property. If a times v vector is 0, then either the scalar a will be 0 or the vector v will be 0. So using these properties you can prove this very easily. Okay, so this I'll give you as homework, you can try it on your own. The proof of this: if a times v vector is equal to 0, then either the scalar a will be 0 or the vector v will be 0. Cool. Okay, so like these are all the derived properties from the properties of vector spaces. All the vector spaces will satisfy these properties as well. You don't need to remember them. Okay. Cool. Now let's see some examples of like another example on vector spaces. Which of the following is or are vector spaces? So there are like lots of vector sets given, and we need to figure out which of them are vector spaces. Okay, so let's start. Okay, so the first vector set given is U, which is set of all xy such that y is equal to 2x. Okay, so let's see. We have U is equal to set of all xy such that y is equal to 2x. Okay, and x and y both are real numbers, so they are doing it over the set of real numbers. Cool. So we need to check, is it a vector space or not. So y is equal to 2x, which means they are not taking all possible points xy, they are just taking the points which are on y is equal to 2x. It is a line passing through origin, right? So y is equal to 2x will look like this. So 0 comma 0 will be there, and y for 1 it will be 2, so it will look something like this. Y is equal to 2x. Okay. Cool. So let's look at the properties again. Only the points on this line is what we are taking, not all the points in R2. Okay, so this is the set that is given. Cool. So again, like what are the properties? V, vector addition. Vector addition will be commutative. So commutative means what? If you have a vector u and a vector v, it should, like their sum should be equal to v plus u. So this should hold true, right? Like commutative and associativity is not a problem. Vector and even associativity should not be a problem. Okay, because vector addition remains same. The addition property remains same, and hence like vector addition property will hold true here, like same for R2. R2 also the property holds. Here also the property will hold, right? Like they will be equal. Now next is E, existence. So we need to check the existence of additive identity. Additive identity. So additive identity is the 0 vector, right? It must be the 0 vector, 0 comma 0, and 0 comma 0 is present inside this set because y is equal to 2x. 0 is equal to 2 times 0, and this is actually present inside this set, and hence additive identity exists. If you add this particular vector to any vector, you will get the same vector back. Okay, so additive identity exists. And additive inverses. So for any vector x comma y, if it is in the set U, then minus x comma minus y should be the additive inverse, right? So if y is equal to 2x, then minus y will be equal to minus of 2x, right? You just multiply with minus 1 on both sides, and hence minus y should be equal to minus 2x, and hence minus x comma minus y will also be in the U. It will also be in the same set. So for example, if you have 1 comma 2 in the set, then minus 1 comma minus 2 will also be in the same set, and hence additive inverses for all elements also exist. They are in the same set. So E is also done. Next is closure. Closure under addition. This is interesting. So if x1 comma y1 is in the set U, and if x2 comma y2 is in the set U, we need to prove that the sum will be x1 plus x2 comma y1 plus y2. Will it be also in the same set U? So if x1 and y1 is in U, which means y1 will be 2 times x1 and y2 should be 2 times x2, because these 2 points are inside the set. And if I add both of them up, we will get y1 plus y2 will be equal to 2 times x1 plus x2, and hence x1 comma x2 comma y1 plus x1 plus x2 and y1 plus y2 will also be in the set U. We just proved it, and hence it is closed under addition. Now closed under scalar multiplication. So if x comma y is in the set U, then if you multiply it with any scalar k, so k times x comma y will be what? It will be kx comma ky. So if y is equal to 2x, then you can multiply both sides by k, you will get ky is equal to 2 times kx, and hence kx comma ky will also be in the same set U, and hence it is closed under scalar multiplication as well, and hence properties of closure is also valid. Now next is the two properties of distribution. So distribution properties will hold true, they hold true for R2, and the same properties should hold here as well. Okay, so the two distribution properties will hold here. Next is the existence of the identity, the scalar multiplication identity. So 1 belongs to this set R, and if you multiply 1 with any vector U, we'll get the same vector back, right? 1 times x comma y will be x comma y, because the scalar multiplication definition is same, and hence O is also satisfied. And the last is rescaling. Rescaling should also hold true, because like if you like just scale a point 2 times, you'll just land it there, or you can just multiply both of them together and then scale. Rescaling should also hold true. And essentially every line passing through origin will be a vector space. We will prove this in the next lecture as well. So yep, actually it is a vector space. So the the set U given here is a vector space. Okay, it is a vector space. Next is set of all possible x comma y such that x is greater than or equal to 0. So here in V, we are just taking, if this is x and this is y, we are taking x is greater than or equal to 0. So we are only taking these points. X must be greater than or equal to, sorry, no, not this. This is y is greater than or equal to 0, right? So what we will be taking is x is greater than or equal to 0, which means all these points. Okay, we are taking only these points. These points are not taken. So here additive identity is existing. But if you notice carefully, additive inverse will not exist, because see, in vector V, what will happen in vector set V, let's say 3 comma 5. 3 comma 5 will be present in the vector space, but its additive inverse will be what? Its additive inverse will be minus 3 comma minus 5, right? So this is 3 comma 5. Minus 3 comma minus 5 is not in V, and hence additive inverses don't exist. It is very clear, right? Additive inverses don't exist in the same set, and hence it is not a vector space. Okay, this is one rule. Even if you are able to find a single rule or a single axiom which is broken, it will not be a vector space. So because of additive inverses, it is not. Cool. Next is set of x, y, z such that x plus y plus z is equal to 0. So it is like in 3-dimensional space, but it is not taking the entire R3. It is essentially a plane in R3, okay, and it is a plane passing through origin. So again, we will prove this in the next lecture. Actually, a plane passing through origin in R3 will also be a vector space. It will be a vector space just like this one. It is a line passing through origin, right? It is also passing through origin. So additive identity exists. 0 comma 0 comma 0 is there, and we can prove the other properties as well. Let's do that. So what is given? X plus y plus z is equal to 0. Okay. So we have W is the set of x, y, z, okay, such that x plus y plus z is equal to 0, and x, y and z are all real numbers, and we are doing it on the vector field R. Okay, cool. So how will we do it? Again, let's see the properties. First is vector Vector addition, like vector addition will be commutative, it will be associative. I don't need to write that because addition, like it is R3, right? Addition properties and scalar multiplication are same. So vector commutative and associativity will be there. Then existence of additive identity 0 comma 0 comma 0 is a part, because 0 plus 0 plus 0 is 0. 0 comma 0 comma 0 is a part of W, and hence additive identity exists. Coming to additive inverses, if x plus y plus z is 0, which means if x, y, z is a part of W, then if you multiply both sides by -1, minus x minus y minus z will also be 0. It means that minus x comma minus y comma minus z will also be a part of W, which means additive inverse for every possible element in the set exists, and it is also part of the same set, and hence additive inverse for all possible elements exist. Next is C, closure under addition. So if x1 plus y1 plus z1 is equal to 0, which means if x1 comma y1 comma z1, which is vector u, is a part of W, then and also x2 plus y2 plus z2 is equal to 0, which means x2, y2, z2 is a part of W, then we can add them both up and we'll get x1 plus x2 plus y1 plus y2 plus z1 plus z2 will also be 0, which means that their addition, the vector addition of these two vectors, x1 plus x2, y1 plus y2 and z1 plus z2 will also be part of W, which means it is closed under addition. And similarly you can prove it is closed under scalar multiplication as well, okay, because k times x1, k times y1, k times z1, their addition will also be 0. You just multiply it by k, and hence k x1, k y1, k z1 will also be part of W. Okay, next is the distributive properties must hold true, because again the scalar multiplication and the definition of addition is not changed, and hence the same properties will hold true here as well. And existence of identity, scalar multiplication identity, which means 1 exists in the set of real numbers, and you multiply 1 with any vector, you will get the same vector back. That because again the definition of scalar multiplication is not changed, so this also holds true. And then rescaling should also work, okay. If you multiply by a and then b, or you multiply by b and then a, the answer won't change, you will land at the same vector, okay. Cool. So all the properties hold true, and yes, it is a vector space, okay. So this W is also a vector space. Now if we look at X, X is a vector set given set of all possible x, y such that x square plus y square is less than or equal to 1. So in X, what they are saying, they are again limiting the search. So if this is xy axis, x square plus y square is less than or equal to 1. It means the circle of size 1, okay. So we are just taking these points. For these points, x square plus y square will be less than or equal to 1. We are only taking the points inside this circle. So here additive identity exists, 0 comma 0 exists, but what will fail? So actually scaling will fail, right? Because for this particular point, if I scale it, then this point does not exist, right? So scaling will fail. So it will not be closed under scale, like it will not be closure under scalar multiplication, that property, okay. C property will fail. How? So if let's say some x comma y, so I can just give you an example, right? Let's say 0.8 comma 0.8, this particular point is part of the vector set x, but if I multiply it with 2 times 0.8 comma 0.8 will be 1.6 comma 1.6, and 1.6 comma 1.6 is not part of the circle, and 1.6 square plus 1.6 square is not less than or equal to 1, and hence it is not a part of x, and hence it is not closed under scalar multiplication, and hence x is not a vector space, okay. And finally, Y is the set of all symmetric 2 cross 2 real matrices, or set of all symmetric 2 cross 2 real matrices. So let's see that. This is interesting. Y. Okay, vector set Y is the set of all 2 cross 2 real symmetric matrices. So how does a symmetric matrix look like? So I can write it like this also. A 2 cross 2 matrix looks like this. So it is set of all matrices and it is symmetric. So let's say if this value is A and this value is B, then this value is C, and then these two values must be equal, right? Because A is equal to A transpose, and hence these two values must be equal. So this is how it will look like. This is how it will look like. Okay, it will have three independent values. So it is a if it is a subspace, if it is a space, it will be a space in three-dimensional space, 3 dimensions. Okay, because there are only three independent values. These two values must be equal. So this is how it will look like, and such that A, B and C are all real numbers, okay, on R. Cool. So these are symmetric matrices. And what do we know about symmetric matrices? We know that anyways, matrix addition is commutative, matrix addition is associative, right? So the first property, vector addition being commutative and associative, must hold true. Next is existence of identity element, additive identity. So the matrix 0, 0, 0, 0 must be the additive identity, right? Because if you add it to any matrix, you'll get the same matrix back. And this is a symmetric matrix. 0, 0, 0, 0 is a symmetric matrix and it will belong to Y because it is symmetric. Because it is symmetric. And hence additive identity exists. And talking about additive inverses, the additive inverse will be for AB, for AC, CB, the additive inverse must be minus A, minus C, minus C, minus B. And if ACCB is a symmetric matrix which is a part of this set, then this is also symmetric, right? Because these two values are equal, and hence this is also a symmetric matrix, and this will also be a part of X, and hence additive inverse also exists. For every matrix, its inverse will also be, which means this matrix will also be a symmetric matrix and it will be part of the set. So this also holds true. Next is closure under addition. So we know this property from matrices that the sum of two symmetric matrices is symmetric. We have proved it, right, in matrices. So sum of two symmetric matrices S1 and S2 will be a symmetric matrix. So you take any matrix here and if you add it to another symmetric matrix which is in this set, the result will also be a symmetric matrix which will also be a part of this set, and that is why it will be closed under addition. And also scalar multiplication of any symmetric matrix will also be a symmetric matrix. You are just multiplying all the values by k. So these two values will still be same, kc and kc, right? And hence it will be closed under scalar multiplication as well. Now the two distributive properties. So for any matrix, the distributive property holds true. We have proved it already, and the definition of scalar multiplication and addition is not changing, and hence the two distributive properties must hold true. The existence of scalar multiplication identity, which means 1. So 1 does belong to the field R, and if you multiply 1 with any matrix, you will get the same matrix back, right? And hence this also holds true. And again, the final one, rescaling, so that also holds true. A times B times any symmetric matrix should be equal to A times B times symmetric matrix, or like you'll get the same matrix essentially, okay? Or B times A times symmetric matrix. Okay, this property is also something that we have seen in matrices. So this also holds true. So yes, actually set of all symmetric matrices is a vector space. We have already seen that set of all 2 cross 2 matrices is also a vector space. But even if you take symmetric matrices, that is also a vector space. Okay. So as a homework, you can try one more. You can try the set of all skew symmetric matrices. Okay. Try to do it on your own. You can try the set of all 2 cross 2 skew symmetric matrices. Is that a vector space or not? You can try that on your own, but this one is, okay. So we have solved this example. U, W and Y are vector spaces, V and X are not vector spaces. Okay, cool. So this actually covers an introduction on vector spaces, what vector spaces are and how do we define them, and what sets actually constitute vector spaces and what not. And we will see more detailed analysis like what are subspaces, span, and a lot of interesting concepts on spaces in the coming lectures. Thanks for watching this lecture. Let's meet in the next one. Bye bye.